There are 2 trillion galaxies in the observable universe, not 2 trillion stars. 2 trillion galaxies, each containing hundreds of billions of stars of their own. The number is so large that if you tried to count every star visible from Earth with the naked eye, you would finish in about 15 minutes. But if you tried to count every star in the observable universe, counting 1 per second without stopping, without sleeping, without pausing for a single breath, it would take you approximately 3,000 trillion years. The universe has only existed for 13.8 billion years. You would need more time than the universe has been alive, multiplied by over 200,000, just to count what is out there. This is where we are going tonight. Through 5 hours of the most extraordinary facts, the most breathtaking discoveries, and the most humbling truths that human beings have ever uncovered about the cosmos. From the burning heart of our own sun to the cold, silence at the edge of everything, from the moons of Jupiter to the last black holes burning at the end of time itself, this journey is for anyone who has ever looked up at the night sky and felt the pull of something larger than themselves. Before we begin, if you are watching this and you love the feeling of drifting off to something bigger than yourself, something that puts every worry and every deadline and every small frustration into a perspective so vast it simply dissolves, then this channel was made for you. Subscribe and hit the notification bell so that the next time we take a journey like this one, you will be there for it. And now, with that said, let us go. The universe did not always exist. There was a time, incomprehensible as it sounds, when there was nothing. No space, no time, no matter, no energy. And then, approximately 13.8 billion years ago, everything began. Not with an explosion in space, as the phrase Big Bang might suggest, but with an expansion of space itself. Space did not exist before this moment, and then suddenly it did, stretching outward in every direction simultaneously, carrying with it everything that would eventually become the galaxies, the stars, the planets, and every living thing that has ever drawn a breath. We will return to the beginning in detail later in this journey. But for now, hold that image. Everything you have ever seen, everyone you have ever known, every mountain and ocean and city and grain of sand, every dinosaur that ever walked the earth, every star you have ever looked up at on a clear night, all of it came from a single event 13.8 billion years ago. And the universe has been expanding ever since, growing larger and colder and more spread out, filling with structure and light and complexity in ways that scientists are still only beginning to understand. We begin our journey not at the edge of the universe, but close to home, with the star that makes our existence possible. The one that rises every morning and that you have seen so many times you may have stopped noticing how extraordinary it is. We begin with the sun. The sun is a star. That sentence is simple enough, but the full weight of it takes a moment to settle. When you look up at the night sky and see thousands of points of light scattered across the darkness, each one of those points is a sun. Some are smaller than ours. Many are larger. Some are burning blue and hot and fierce. Others are old and swollen and red. The universe is full of stars, and ours is one of them, a medium-sized yellow dwarf sitting in an unremarkable position about 2/3 of the way out from the center of the Milky Way galaxy. But unremarkable in cosmic terms does not mean small. The Sun contains 99.86% of all the mass in the entire solar system. Every planet, every moon, every asteroid, every comet, every particle of dust floating between the worlds, all of it together makes up just 0.14% of the solar system's total mass. The Sun is not just the center of our solar system, it is almost entirely what our solar system is made of. At its core, the Sun is a nuclear fusion reactor of unimaginable scale. The temperature at the center reaches approximately 15 million degrees Celsius. Under that heat and the crushing weight of the sun's own gravity, hydrogen atoms are forced together with enough energy to fuse, forming helium and releasing an enormous burst of energy in the process. Every single second, the sun converts approximately 600 million tons of hydrogen into helium. Every second. The energy released by this process travels outward through the sun's interior, a journey that can take anywhere from 10,000 to 100,000 years just to reach the surface, after which it races across 93 million miles of empty space and arrives at Earth in just over 8 minutes. That sunlight warming your face on a summer afternoon may have started its journey inside the sun before the first modern humans walked the Earth. The photons leaving the sun's surface today began their lives as energy created in the core tens of thousands of years ago, bouncing and scattering through the dense solar interior before finally escaping into space and making that last 8-minute dash to wherever they land. Every ray of sunlight carries within it a record of ancient processes, happening at depths no instrument has ever penetrated. The surface of the sun, called the photosphere, burns at approximately 5,500 degrees Celsius. That is extraordinarily hot by any earthly standard. But here is something that genuinely puzzled scientists for decades. The corona, the sun's outer atmosphere, which extends millions of kilometers into space, is far hotter than the surface. While the photosphere sits at 5,500 degrees, the corona reaches temperatures of 1 to 3 million degrees Celsius. Heat should decrease with distance from a source. The fact that the sun's atmosphere gets hotter as you move away from the surface appears to violate basic physics. And while scientists now have leading theories involving magnetic waves and nano-flares, the coronal heating problem is not fully resolved. The sun has been burning for 4.6 billion years, and it is still keeping secrets. The sun is not a passive, static object. It is alive with activity. Sunspots are dark patches on the surface where intense magnetic fields suppress the flow of heat from the interior, making those regions cooler and therefore darker than their surroundings. They are temporary, lasting anywhere from a few days to a few months, and they appear and disappear in cycles. Approximately every 11 years, the sun moves from a period of relative quiet, called solar minimum, to a peak of activity called solar maximum, during which sunspots multiply, solar flares become more frequent, and the sun's behavior becomes more dynamic and more dangerous. Solar flares are intense bursts of radiation caused by the sudden release of magnetic energy from the sun's surface. When a powerful flare occurs, it can disrupt radio communications on Earth within minutes, interfere with GPS systems, and increase radiation exposure for astronauts and airline passengers flying polar routes. But flares are only one part of the sun's arsenal. Coronal mass ejections, or CMEs, are even more dramatic. A CME is a massive cloud of magnetized plasma hurled from the sun's surface, sometimes containing billions of tons of charged particles moving at millions of kilometers per hour. When a CME reaches Earth, it interacts with our planet's magnetic field, sometimes causing geomagnetic storms that can damage satellites, trip power grid transformers, and paint the night sky with auroras visible far beyond the polar regions where they normally appear. In September of 1859, the most powerful geomagnetic storm in recorded history struck Earth. It is known as the Carrington event, named after the British astronomer Richard Carrington, who observed the solar flare that caused it. The storm was so intense that telegraph systems across Europe and North America failed completely, with some operators receiving electric shocks from their equipment. Telegraph lines that were disconnected from their power sources continued to transmit messages spontaneously, powered entirely by the geomagnetic current in the air. Auroras were seen as far south as Cuba, the Bahamas, and Hawaii. People in the northeastern United States could read newspapers by the light of the aurora at midnight. If a storm of equivalent magnitude struck Earth today, the damage to modern electrical infrastructure could be catastrophic. Satellites could be disabled. Power grids could fail across entire continents. The recovery time has been estimated at years rather than weeks. The sun that rises every morning and warms every living thing on this planet is also, if the conditions are right, capable of bringing our technological civilization to its knees in a matter of hours. Scientists monitor the sun continuously from both ground-based observatories and space-based instruments precisely because of this threat. And early warning systems are in place to give power grid operators and satellite operators time to take protective measures when a major CME is detected heading toward Earth. In 2018, NASA launched the Parker Solar Probe, a spacecraft designed to fly closer to the Sun than any human-made object in history. The probe has since broken its own records repeatedly, skimming through the Sun's corona at distances as close as 6.1 million kilometers from the surface, well inside the orbit of Mercury. To survive these passes, the probe is shielded by a carbon composite heat shield, roughly 11 centimeters thick, which faces temperatures exceeding 1,300 degrees Celsius, while the instruments behind it remain at room temperature. The Parker Solar Probe has also broken the record for the fastest human-made object ever, reaching speeds of approximately 690,000 kilometers per hour during its closest approaches to the Sun. It is giving scientists the first direct measurements of the solar wind and the corona from within, and the data it is returning is already reshaping our understanding of our star. The solar wind that the Parker Solar Probe is studying is the constant stream of charged particles flowing outward from the Sun in every direction. This wind fills the entire solar system and beyond, creating a vast bubble of influence called the heliosphere. It is the solar wind that causes the tails of comets to always point away from the Sun, regardless of the direction the comet is traveling. It is the solar wind interacting with Earth's magnetic field that creates the auroras, those shimmering curtains and ribbons of green and red and purple light that dance across the polar skies. The auroras are one of the most beautiful phenomena on Earth, and their beauty is a direct product of violence. When charged particles from the solar wind are funneled by Earth's magnetic field toward the poles, they collide with atoms and molecules in the upper atmosphere, exciting those atoms and causing them to release energy as light. Oxygen at lower altitudes produces the most common green glow. Oxygen at higher altitudes produces a rarer deep red. Nitrogen contributes blues and purples. The specific mix of colors in any given aurora display depends on the altitude and the intensity of the particle bombardment. On nights when a powerful CME has struck Earth, auroras have been seen as far south as Texas and Florida, lighting up the sky in colors that people who have never seen them before do not have words for. The aurora borealis and the aurora australis, the northern and southern lights respectively, have been the subject of wonder and mythology across human cultures for as long as people have lived at high latitudes. The Norse saw them as the reflections of the shields of the Valkyries. Indigenous cultures across the Arctic have their own traditions and stories attached to these lights. Today we understand the physics perfectly, but understanding the mechanism does nothing to diminish the experience of standing outside on a clear winter night and watching the sky come alive with color. Some experiences remain awe-inspiring regardless of how completely they are explained. The sun has been burning for 4.6 billion years. In approximately 5 billion more years, it will begin to run low on hydrogen fuel in its core. As the core contracts under gravity, the outer layers will expand dramatically, transforming the sun into a red giant. In this phase, the sun will swell to a size that likely engulfs Mercury and Venus, and possibly Earth as well, though by that time Earth's surface will already have been sterilized by the gradually increasing solar luminosity long before the expansion begins. The red giant phase will last for roughly 1 billion years, after which the Sun will shed its outer layers in a beautiful expanding shell of gas called a planetary nebula, and the remaining core will collapse into a small, incredibly dense object called a white dwarf, no larger than Earth, but containing the full mass of the Sun. The white dwarf will slowly cool over trillions of years, a fading ember of what was once our star. But that ending is so far in the future that it is almost meaningless to contemplate in human terms. For now, the Sun rises every morning. It will rise tomorrow. It has been rising for longer than the Earth has existed, and every photon of light it sends our way has traveled 93 million miles to reach us. Every sunrise is, in the most literal sense, a message from a nuclear furnace 93 million miles away, arriving precisely on schedule. To understand the Sun, we must understand where it came from. And to understand that, we must go back to a time before the solar system existed, to a vast cloud of gas and dust drifting through the Milky Way galaxy approximately 4.6 billion years ago. This cloud, called a molecular cloud, was composed primarily of hydrogen and helium, with traces of heavier elements forged in stars that had lived and died before our solar system was born. For perhaps millions of years, the cloud simply drifted, slowly, quietly, held together loosely by its own gravity. Then something disturbed it. The leading theory suggests a nearby supernova, the explosive death of a massive star, sent a shock wave rippling through the cloud. The shock wave compressed the gas and dust, tipping the balance between the outward pressure of the gas and the inward pull of gravity. Gravity won. The cloud began to collapse. As it collapsed, it began to spin, a consequence of the conservation of angular momentum, the same physical principle that makes a spinning ice skater speed up when they pull their arms in. As the cloud shrank, it spun faster and faster, and the spinning caused the collapsing material to flatten into a disk, with the densest region accumulating at the center. Over hundreds of thousands of years, this central region grew hotter and denser as more material fell onto it, until eventually the pressure and temperature at the core became high enough for nuclear fusion to ignite. Our Sun was born. The remaining material in the surrounding disk did not disappear. It continued to orbit the young Sun, and within this protoplanetary disk, particles began to collide and stick together. Dust grains clumped into pebbles. Pebbles clumped into boulders. Boulders grew into planetesimals, the building blocks of planets ranging in size from meters to hundreds of kilometers. Over millions of years, these planetesimals continued to collide and merge, growing into the protoplanets that would eventually become the 8 planets we know today. The process was not orderly or gentle. The early solar system was a violent place, full of collisions, near misses, and gravitational interactions that flung objects across enormous distances. In the inner solar system, where temperatures were high enough only for rock and metal to condense out of the disk, the terrestrial planets formed. In the outer solar system, where it was cold enough for ice to exist, larger objects accumulated more material and grew into the gas and ice giants. The construction of our solar system took roughly 100 million years from the collapse of the molecular cloud to something resembling the arrangement we see today. But the early solar system was not yet finished with its violence. For a period lasting from approximately 4.1 to 3.8 billion years ago, known as the Late Heavy Bombardment, the inner solar system was subjected to an intense rain of asteroids and comets. The Moon's heavily cratered surface is the most visible record of this period. Mercury's cratered surface tells the same story. Earth was struck repeatedly, and scientists believe that many of the impacts during this period may have delivered water and organic molecules to our planet from the outer solar system, where ice was abundant. The water in the oceans you have seen, the water in your own body, may have arrived on Earth riding inside asteroids and comets that formed in the cold outer reaches of the solar system billions of years ago. The late heavy bombardment was not a gentle drizzle. Some of the impactors were hundreds of kilometers across. The energy released by the largest impacts was sufficient to vaporize oceans, melt surface rock across entire hemispheres, and temporarily render the surface of the Earth completely inhospitable to any life that might have been developing. And yet, in the geological record, we find evidence that life began on Earth remarkably soon after the bombardment ended, possibly as early as 3.5 to 3.8 billion years ago. Either life survived the bombardment in protected niches deep underground or in deep ocean hydrothermal vents, or it re-emerged with remarkable speed after the worst of the impacts subsided. Either way, the story of life on Earth begins in the immediate aftermath of one of the most violent periods in the history of the solar system. There is a philosophical dimension to all of this that is worth sitting with for a moment. The Sun is a third-generation star. That means the atoms inside it were not created in the Big Bang. They were forged in the cores of stars that lived and died before our Sun was born, scattered into space by supernovae, gathered into new clouds, collapsed into new stars, and scattered again. The carbon in your body was made inside a star that no longer exists. The iron in your blood was forged in the core of a star that exploded before the solar system formed. The oxygen you are breathing right now was created in stellar furnaces billions of years ago. We are not just living on a planet in a solar system in a galaxy. We are made of the remnants of dead stars. Every atom in your body has been part of something else, something that burned and collapsed and scattered its contents into the void before being gathered up again into the unlikely arrangement that is you. The 4 planets closest to the Sun are called the terrestrial planets, or the rocky planets. They are Mercury, Venus, Earth, and Mars. Each one is a world of extremes. Each one tells a story about what happens when a planet forms in a particular location with a particular set of conditions, and each one, in its own way, is a reminder of how improbable and how fragile the conditions for life actually are. Mercury is the closest planet to the Sun, and in many ways it is the most extreme of the 4. It is a small world, only slightly larger than Earth's moon, with a surface that has been battered into a cratered landscape over billions of years of impacts. Because Mercury has virtually no atmosphere to moderate its temperature, the swings between day and night are the most dramatic of any planet in the solar system. On the sunlit side, temperatures can reach nearly 430 degrees Celsius. On the night side, they plunge to negative 180 degrees Celsius. These are not seasonal changes. This is the temperature difference between noon and midnight on the same planet. For a long time, Mercury was considered geologically dead, a cold, cratered relic with little to interest planetary scientists beyond its proximity to the Sun. The Messenger spacecraft, which orbited Mercury from 2011 to 2015, completely changed that picture. Among its many discoveries, Messenger confirmed the existence of water ice in the permanently shadowed craters near Mercury's North Pole. Mercury, the closest planet to the Sun, a world where the surface can exceed 400 degrees Celsius, has water ice. The ice survives because the craters near the poles are so deep and their walls so steep that sunlight never reaches the floor. In those perpetual shadows, temperatures remain cold enough for ice to persist for billions of years. The water may have been delivered by comets and asteroids over the history of the solar system, and because Mercury has no atmosphere to cause it to sublimate away, it simply stays. Messenger also revealed that Mercury has an enormous iron core relative to its size, taking up approximately 85% of the planet's radius. By comparison, Earth's core takes up about 54%. The leading theory is that Mercury once had a much larger rocky mantle, but a giant impact early in the solar system's history stripped away much of the outer layers, leaving behind the disproportionately large core we see today. Mercury is, in a sense, the exposed core of a planet that once was larger. The European Space Agency's Bepi Colombo mission, launched in 2018, is currently en route to Mercury and will enter orbit in 2025, with the goal of studying the planet's surface, magnetic field, and interior structure in far greater detail than MESSENGER could achieve. Mercury also has one of the most unusual day-length relationships of any planet. Because its rotation is tidally influenced by the Sun's gravity, Mercury rotates exactly 3 times for every 2 orbits around the Sun, a resonance known as a 3-to-2 spin-orbit resonance. This means that a solar day on Mercury, the time from one sunrise to the next, is actually twice as long as a Mercurian year. The Sun rises, moves across the sky very slowly, stops, reverses briefly, then continues to the horizon. If you were standing on Mercury near its equator, you would see the Sun rise, inch part way across the sky, stop, appear to briefly move backward toward the horizon, and then continue forward again. The gravitational dance between Mercury and the Sun creates a sky spectacle unlike anything seen from Earth or any other planet. Venus is almost exactly the same size as Earth. It is often called Earth's twin, and in terms of mass and diameter, the comparison is fair. But the similarity ends there. Venus is a world that went catastrophically wrong, and understanding why is one of the most important questions in planetary science, because Earth could, under different circumstances, have followed the same path. The surface of Venus sits beneath a dense atmosphere of carbon dioxide 90 times thicker than Earth's atmosphere, with clouds of sulfuric acid swirling at altitude. The greenhouse effect on Venus is so extreme that the surface temperature is approximately 465 degrees Celsius, hot enough to melt lead, and hot enough that it barely varies between day and night, or between the equator and the poles. Venus is hotter than Mercury, despite being farther from the Sun, purely because of the runaway greenhouse effect that has taken hold in its atmosphere. The Soviet Union sent a series of spacecraft called Venera to Venus between the 1970s and 1980s, and these probes represent some of the most remarkable engineering achievements in the history of space exploration. Landing on Venus means descending through sulfuric acid clouds, surviving the crushing atmospheric pressure at the surface, which is equivalent to being 900 meters underwater on Earth, and operating in temperatures that would destroy most electronics within minutes. The engineers who designed the Venera landers had to build spacecraft that could survive these conditions long enough to take photographs, conduct chemical analyses, and transmit data back to Earth, all while being slowly cooked and crushed by the environment. The Venera 13 lander, which touched down on Venus in March 1982, survived for 127 minutes before being destroyed by the environment. In that time, it transmitted the first color photographs of the Venusian surface, a bleak, orange-lit landscape of flat rocks and slabs, with the sky glowing a dim amber from the thick atmosphere above. The photographs revealed a surface that was geologically active, with evidence of relatively recent volcanic activity. Venus may still be volcanically active today. Data from the Magellan spacecraft in the 1990s, combined with recent reanalysis of Venera data, suggests that volcanic eruptions may be occurring on Venus right now, adding fresh lava to the surface and releasing gases into the already dense atmosphere. Venus also rotates backward compared to most planets in the solar system. If you could stand on the surface of Venus, the Sun would rise in the west and set in the east. And Venus rotates so slowly that a single Venusian day is actually longer than a Venusian year. It takes 243 Earth days for Venus to complete one rotation, but only 225 Earth days to complete one orbit around the Sun. The day is longer than the year, The reason for this retrograde rotation is not fully understood. The leading theories involve a large impact early in Venus's history, or a gradual slowing and reversal of rotation due to tidal forces from the Sun combined with atmospheric dynamics. But neither explanation is entirely satisfying, and the question of why Venus rotates the way it does remains open. Earth, of course, is the world we know, but it is worth pausing to appreciate just how unusual it is, because the more we learn about the other planets in our solar system and beyond, the more exceptional Earth appears. It has liquid water on its surface, which requires a very specific temperature range maintained by a very specific atmospheric composition. It has a large moon that stabilizes its axial tilt, preventing the kind of extreme climatic swings that would occur if the planet wobbled freely. It has a strong magnetic field generated by its molten iron core, which deflects the solar wind and protects the atmosphere from being stripped away, as has happened on Mars. It has plate tectonics, which recycle carbon from the atmosphere into the crust and back again, acting as a long-term thermostat for the climate. It has an atmosphere with just the right mix of gases to be breathable by complex life. All of these features coexist on Earth, and the probability of all of them occurring together in the same place is, by any reasonable estimate, extraordinarily small. The more planetary scientists study the other worlds of the solar system and the exoplanets beyond it, the more a picture emerges of Earth as a world that has been extraordinarily fortunate, not in any mystical sense, but in the purely statistical sense that it formed in the right place, with the right mass, at the right time, and experienced the right sequence of events over 4.5 billion years to produce conditions capable of sustaining complex life. Most worlds, most of the time, are not like this. Mars is the fourth planet from the Sun, and it is the planet that human beings have most thoroughly explored beyond Earth. It is a cold, dry, thin-aired world with a surface pressure less than 1% of Earth's, but it is also a world with a dramatic geological history, a past that includes rivers, lakes, and possibly oceans, and a future that may one day include human settlers. The most obvious feature of Mars is its color. The planet's reddish-orange hue comes from iron oxide, essentially rust, covering much of its surface. Mars rusted because it once had water, and water plus iron plus oxygen produces rust. The rust itself is evidence of a wetter past. But the evidence does not stop at the color of the soil. The Martian landscape is carved with channels, valleys, and basins that can only have been formed by the flow of liquid water. Ancient riverbeds wind across the surface. Impact craters contain sedimentary layers that formed at the bottom of ancient lakes. The northern lowlands of Mars may once have been covered by an ancient ocean that existed for hundreds of millions of years before the planet's magnetic field collapsed, allowing the solar wind to gradually strip away the atmosphere and the water that depended on it. Mars is home to the largest volcano in the solar system, Olympus Mons. It stands approximately 22 kilometers above the Martian surface, which is roughly 2.5 times the height of Mount Everest above sea level on Earth. But the truly staggering thing about Olympus Mons is not its height, but its width. The volcano is approximately 600 kilometers across at its base. If you stood at the base of Olympus Mons and began walking toward its center, the summit would be so far away and the slope so gradual that the volcano would not even appear as a mountain. The terrain would simply seem to be rising very gently, and the summit, over 20 kilometers above you, would be well beyond the horizon. The entire base of Olympus Mons is ringed by cliffs up to 8 kilometers high, where the volcano's edge drops away sharply from the surrounding plains. Olympus Mons is so large that it could cover the entire state of Arizona 3 times over. Mars also hosts the largest canyon system in the solar system, Valles Marineris. Stretching approximately 4,000 kilometers from east to west, Valles Marineris would span the entire continental United States from coast to coast. At its widest, it is up to 600 kilometers across, and it reaches depths of up to 8 kilometers. By comparison, the Grand Canyon in Arizona is about 446 kilometers long, 29 kilometers wide, and just over 1.5 kilometers deep. Valles Marineris makes the Grand Canyon look like a scratch on the surface. The canyon system was not carved by water. It formed through tectonic processes as the Martian crust was stretched and fractured by volcanic activity over billions of years. The evidence that Mars once had liquid water is now overwhelming. NASA's Curiosity rover, which landed in Gale Crater in 2012, found ancient riverbeds and lake sediments within the crater, confirming that it once held a lake with liquid water for potentially millions of years. The Perseverance rover, which landed in Jezero Crater in 2021, is exploring a site that was once an ancient river delta, where a river flowed into a lake and deposited sediments over a long period of time. Those sediments are exactly the kind of environment where microbial life might have left behind chemical traces, called biosignatures, if it ever existed on Mars. Perseverance is collecting rock and soil samples and sealing them in small metal tubes that will eventually be collected by a future mission and returned to Earth for analysis. This Mars sample return mission, planned as a joint project between NASA and the European Space Agency, may deliver the samples to Earth laboratories sometime in the 2030s. If those samples contain chemical or morphological evidence of ancient microbial life, it will be the most consequential scientific discovery in human history. If they contain no such evidence, that too will be scientifically important, telling us something profound about the conditions under which life does and does not arise. The question of whether Mars ever had life, and whether anything might still exist in protected niches deep underground where liquid water might persist today, is one that we do not yet have an answer to. But we are closer to finding out than we have ever been. If this is the first time you are hearing some of these facts, drop a comment below and tell us which one stopped you in your tracks. Whether you are wide awake and deep into curiosity, or you are listening with your eyes closed and letting these ideas drift through your mind, we want to hear from you. And now, let us keep going. Beyond the rocky inner planets, the solar system opens up into a different scale entirely. The outer planets are giants, not just larger than the rocky worlds, but categorically different in composition, structure, and behavior. And of all the outer planets, none is more dominant, more dramatic, or more important to the solar system as a whole than Jupiter. Jupiter is the largest planet in the solar system by a wide margin. It is more than twice as massive as all the other planets combined. Its diameter is approximately 11 times that of Earth, and over 1,300 Earths could fit inside it. Despite this enormous size, Jupiter is not a solid world. It is composed almost entirely of hydrogen and helium, with no definite solid surface. As you descend through Jupiter's atmosphere, the pressure increases until the hydrogen is compressed into a liquid, and then, deeper still, into a metallic state in which hydrogen behaves like a metal, conducting electricity and generating Jupiter's massive magnetic field, which is the strongest of any planet in the solar system. The most famous feature of Jupiter is the Great Red Spot, a storm that has been raging in the planet's southern hemisphere for at least 350 years, and possibly much longer. The Great Red Spot is a high-pressure anticyclone, a storm that rotates in the opposite direction from the hurricanes we experience on Earth, and it is powered by Jupiter's enormous internal heat. Jupiter radiates more energy than it receives from the Sun, generating heat internally from the slow gravitational compression of its interior. This internal heat drives the convective currents that fuel the storm systems in the atmosphere, including the Great Red Spot. When astronomers first began measuring the Great Red Spot in the 19th century, it was approximately 40,000 kilometers across, large enough to fit 3 Earths inside it, side by side. Today, After more than a century of shrinking, it measures approximately 14,000 kilometers across. It is still larger than Earth, but the trend is clear, and scientists are watching it carefully. Whether the Great Red Spot will continue to shrink and eventually dissipate, or whether it will stabilize and persist for another few centuries, is something we do not yet know. Some models suggest that the storm may be drawing energy from smaller storms that it absorbs, potentially sustaining itself even as it shrinks. Others suggest it is in terminal decline. Jupiter's role in the solar system extends far beyond its visual drama. Its enormous gravitational influence has shaped the structure of the solar system over billions of years. The asteroid belt between Mars and Jupiter exists in its current fragmented state, largely because Jupiter's gravity prevented those objects from ever coalescing into a planet. More importantly, Jupiter acts as something of a gravitational shield for the inner solar system. Its mass attracts and captures some comets and asteroids that would otherwise be on trajectories that could bring them into the inner solar system and potentially strike Earth. In 1994, astronomers watched as comet Shoemaker-Levy 9, which had been torn apart by Jupiter's gravity into a string of 21 fragments, crashed into Jupiter over the course of 6 days. The impacts left dark scars in Jupiter's atmosphere larger than Earth that persisted for weeks. It was a vivid demonstration of what Jupiter intercepts so that the inner solar system does not have to. Jupiter is also surrounded by an extraordinary collection of moons. At least 95 moons have been confirmed in orbit around Jupiter, more than any other planet in the solar system. The 4 largest, discovered by Galileo Galilei in 1610 and known as the Galilean moons, are worlds in their own right. Io, Europa, Ganymede, and Callisto are each individually remarkable, and we will explore them in detail shortly. Ganymede, the largest moon of Jupiter, is also the largest moon in the solar system, and it is larger than the planet Mercury. It has its own magnetic field, the only moon in the solar system known to do so. Callisto, the outermost of the Galilean moons, is the most heavily cratered object in the solar system, and is believed to have a liquid water ocean beneath its ancient, cratered surface. Saturn is the second largest planet and the most visually distinctive object in the solar system. Even through a small telescope, Saturn's rings are immediately recognizable, and seeing them for the first time through an eyepiece is one of the most consistently reported, awe-inspiring experiences in amateur astronomy. People who have seen it often describe a moment of disbelief, feeling that what they are seeing cannot be real, that it looks too perfect, too geometrically precise, too much like a picture to be an actual object floating in space. The rings extend up to 280,000 kilometers from the planet, yet they are remarkably thin. In most places, the rings are no more than a few hundred meters thick, and in some regions, as thin as 10 meters. If you were to scale the rings down to the size of a sheet of paper in terms of their thickness-to-width ratio, that sheet of paper would need to be roughly the size of a football field. They are almost impossibly flat relative to their enormous extent. The rings are composed of countless individual particles of water, ice, and rock, ranging in size from tiny grains smaller than a grain of sand to boulders several meters across. These particles orbit Saturn just as moons orbit a planet, each one following its own individual orbit, and the rings are shaped and maintained by gravitational interactions between the particles themselves and Saturn's many moons. Some of Saturn's smaller moons, called shepherd moons, orbit just inside or outside the edges of the rings, and their gravity corrals the ring particles, keeping the edges sharp and preventing them from spreading. The moons Prometheus and Pandora, for example, shepherd the narrow F ring, one of the outermost rings, maintaining its braided and kinked structure through their gravitational influence. One of the most surprising discoveries about Saturn's rings is how young they are. Based on analysis of data from the Cassini spacecraft, Scientists now believe that Saturn's rings are somewhere between 10 and 100 million years old, which is extremely young in geological and astronomical terms. The dinosaurs were already on Earth when Saturn's rings likely formed, possibly from the breakup of a moon or the capture and destruction of a comet or asteroid that wandered too close. In another 100 million years or so, the rings will likely be gone, pulled gradually inward by Saturn's gravity and by the drag of charged particles from Saturn's upper atmosphere. The iconic rings of Saturn are a temporary feature. Future civilizations, if any exist in the far future, may look at Saturn and see only a plain gas giant with no rings at all. The Cassini spacecraft, a joint mission between NASA, the European Space Agency, and the Italian Space Agency, spent 13 years in orbit around Saturn between 2004 and 2017. It was one of the most productive and scientifically rich missions in the history of planetary exploration. Among its countless discoveries, Cassini found evidence of a subsurface ocean on Saturn's moon Enceladus, detected complex organic molecules in the geysers erupting from that moon, mapped the lakes of liquid methane on Titan, discovered 6 new moons of Saturn, and revealed previously unknown details about the structure and composition of Saturn's rings. In September 2017, with its fuel nearly exhausted, NASA deliberately flew Cassini into Saturn's atmosphere, destroying the spacecraft to prevent any possibility of it contaminating Saturn's moons with Earth microbes. The decision to end the mission this way was made specifically to protect Enceladus and Titan, both of which have been identified as potentially habitable environments. If Cassini were allowed to drift uncontrolled after running out of fuel, there was a small but non-zero chance it could eventually crash onto one of these moons and contaminate it with any Earth microbes that had survived the journey despite sterilization efforts. The mission's final transmission was received on September 15, 2017. Cassini had been a visitor to the Saturnian system for 13 years, and its end was, by any measure, a fitting one. It became part of the planet it had spent so long studying. Beyond Saturn, the solar system changes character. The 2 outermost planets, Uranus and Neptune, are sometimes called the ice giants to distinguish them from the gas giants Jupiter and Saturn, because their interiors are believed to contain large amounts of water, methane, and ammonia in a high-pressure exotic state, rather than being predominantly hydrogen and helium. Uranus is the 7th planet from the Sun, and it is perhaps the most peculiar in terms of its orientation. While most planets spin on axes that are roughly perpendicular to the plane of the solar system, tilted by anywhere from a few degrees to about 30 degrees, Uranus is tilted at 98 degrees. It essentially rotates on its side, like a ball rolling along the ground rather than spinning like a top. The most widely accepted explanation is that Uranus was struck by an Earth-sized object early in the solar system's history, and the impact knocked it over. A more recent hypothesis suggests it may have been the result of 2 separate, smaller impacts, which would explain why the planet is tilted the way it is, while still retaining most of its original rotational momentum. The consequences of this extreme axial tilt are extraordinary. Each pole of Uranus experiences approximately 42 years of continuous sunlight, followed by 42 years of complete darkness. During the summer at the North Pole, the sun never sets. During the winter, it never rises. The seasonal extremes on Uranus are the most dramatic of any planet in the solar system, and the atmospheric dynamics that result from these conditions are still not fully understood. When the Voyager 2 spacecraft flew past Uranus in 1986, it was during the Uranian Southern Hemisphere summer, and the South Pole was pointed almost directly towards the Sun. The spacecraft found the planet's atmosphere to be remarkably bland compared to Jupiter and Saturn, with few visible storms or banding. Scientists believe this may change as Uranus moves through its seasons, and ground-based observations have since detected storms and cloud activity increasing as the planet approaches equinox. Uranus is also notable for being the only planet in the solar system whose moons are named after characters from the works of William Shakespeare and Alexander Pope. Titania, Oberon, Miranda, Ariel, Umbriel, and more than 20 others all take their names from these literary sources, a tradition that sets Uranus's moon system apart from every other planet. Miranda, the smallest of the major Uranian moons, has one of the most geologically tortured surfaces in the solar system, with cliffs up to 20 kilometers high, thought to be among the tallest cliffs in the solar system. The origin of Miranda's chaotic landscape is not fully understood. One theory suggests it was broken apart and reassembled by an ancient impact. Neptune is the 8th and farthest planet from the Sun, a deep blue world of extraordinary atmospheric violence. Its color comes from methane in its atmosphere, which absorbs red light and reflects blue. But the most striking thing about Neptune is not its color, it is its winds. Neptune has the fastest winds of any planet in the solar system, with measured speeds exceeding 2,100 kilometers per hour at some latitudes. To put that in perspective, the most powerful hurricanes on Earth have sustained winds of around 300 kilometers per hour. Neptune's winds are 7 times faster than Earth's most extreme storms, and they blow in a world where the average temperature is negative 214 degrees Celsius. The reason for Neptune's extreme winds is one of the solar system's enduring mysteries. At its distance from the Sun, Neptune receives very little solar energy, far less than the inner planets. Yet instead of being calm, its atmosphere is among the most dynamic in the solar system. The leading explanation involves Neptune's internal heat. Like Jupiter, Neptune radiates more energy than it receives from the Sun, suggesting a significant internal heat source, likely the slow gravitational compression of its interior. This internal heat drives convective currents and storm systems in the atmosphere, generating the ferocious winds observed. But the precise mechanism that produces winds of this speed in this kind of atmosphere is not fully explained, and Neptune remains one of the least understood planets in the solar system. The only spacecraft to have visited Neptune is Voyager 2, which flew past the planet in August 1989. In the 12 hours of its closest approach, Voyager 2 returned more data about Neptune than had been gathered by every telescope on Earth in the preceding centuries. It revealed a complex, dynamic world with dark storm systems, a system of faint rings, and a collection of moons, including the extraordinary Triton. After its Neptune flyby, Voyager 2 continued outward, leaving the solar system entirely. It is now in interstellar space, over 19 billion kilometers from the Sun, still transmitting data back to Earth, though the signal takes approximately 17 hours to make the journey each way. Beyond Neptune lies a region of the solar system that most people have heard of, but relatively few can describe in detail. The Kuiper Belt is a vast disk of icy objects extending from Neptune's orbit outward to roughly 50 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, approximately 150 million kilometers. So the Kuiper Belt stretches from 30 to 50 times that distance. It is somewhat like the asteroid belt between Mars and Jupiter, but far larger, far colder, and composed primarily of ice rather than rock. The Kuiper Belt contains perhaps trillions of objects, ranging from tiny ice grains to dwarf planets hundreds of kilometers across. Pluto is the largest known object in the Kuiper Belt. It was discovered in 1930 and classified as a planet for 76 years, until the International Astronomical Union redefined the criteria for planethood in 2006 and reclassified it as a dwarf planet. The reclassification was controversial, and it remains a topic of debate, but the scientific reasoning was sound. Pluto has not cleared its orbital neighborhood of other objects, which is one of the 3 criteria the IAU requires for full planet status. What Pluto has, however, is a surprising complexity. The New Horizons spacecraft, launched in 2006, flew past Pluto in July 2015 after a journey of 9.5 years. The images it returned were extraordinary. Scientists had expected Pluto to be a simple, crater-covered ice ball, geologically dead. Instead, New Horizons revealed a geologically active world with towering mountains of water ice rising up to 3.5 kilometers, vast, smooth plains of nitrogen ice that appear to be geologically young, and a heart-shaped glacier called Tombor Regio, named after Clyde Tombaugh, the astronomer who discovered Pluto. Tombor Regio is larger than Texas and Oklahoma combined. The smoothness of the nitrogen ice plains suggests they have been resurfaced relatively recently, within the last 100 million years, indicating that geological processes are still active on Pluto despite its distance from the Sun. Beyond the Kuiper Belt lies a theoretical structure called the Oort cloud. Unlike the Kuiper Belt, which has been directly observed, the Oort cloud has never been seen. It is inferred from the behavior of long-period comets that travel on orbital paths so elongated that they take thousands or even millions of years to complete one orbit. These comets appear to come from a roughly spherical cloud of icy objects surrounding the solar system at distances between 2,000 and 100,000 astronomical units from the Sun. The outer edge of the Oort cloud is estimated to be about a quarter of the way to the nearest star. If the solar system has a boundary, the Oort cloud is approximately where it lies. Now we come to some of the most scientifically compelling objects in the solar system and some of the most promising places to search for life beyond Earth. The moons of the outer planets are worlds of extraordinary diversity, and several of them have captured the attention of astrobiologists and planetary scientists in ways that no other objects in the solar system have, with the possible exception of Mars. Jupiter's moon Europa is one of the most intensely studied objects in the solar system, and for good reason. Europa is slightly smaller than Earth's moon and covered in a shell of water ice, but beneath that ice lies a global ocean of liquid salt water, kept liquid by tidal heating from Jupiter's gravity. The tidal forces from Jupiter flex and squeeze Europa's interior as the moon orbits, generating heat through friction, enough heat to keep the ocean liquid despite Europa's enormous distance from the Sun. The ocean beneath Europa's ice shell is estimated to contain twice as much liquid water as all of Earth's oceans combined. It has likely been liquid for billions of years. The ice shell above it may be only a few kilometers thick in places, and where it cracks, material from below can sometimes seep upward. Measurements from the Hubble Space Telescope and the Galileo spacecraft have detected what appear to be water vapor plumes erupting from Europa's surface, similar to the geysers on Enceladus, suggesting that material from the subsurface ocean is being vented directly into space. If this is confirmed, it means that a future spacecraft could potentially fly through these plumes and directly sample the chemistry of Europa's ocean without needing to drill through the ice. The question at the heart of Europa science is whether the ocean below the ice could support life. On Earth, we know that life exists around hydrothermal vents on the ocean floor, far from any sunlight, powered entirely by chemical energy from the planet's interior. These deep-sea ecosystems were completely unknown until they were discovered in 1977, and their discovery transformed our understanding of the range of environments in which life can exist. Europa's ocean, in contact with a rocky seafloor, heated by tidal forces, and containing the chemical ingredients necessary for life, is considered by many scientists to be the most promising candidate for extraterrestrial life in our solar system. NASA's Europa Clipper mission, launched in October 2024, is on its way to Jupiter and will arrive in 2030 to conduct detailed studies of Europa. The spacecraft will perform 49 close flybys of Europa, passing as close as 25 kilometers above the surface, and will use its suite of scientific instruments to characterize the ice shell, the ocean beneath it, and the chemistry of any material being vented into space. If Europa Clipper finds strong evidence that the ocean is habitable, it will lay the groundwork for a future lander mission that could actually set down on Europa's surface and attempt to drill into the ice. Saturn's moon Titan is an entirely different kind of world, and in some ways even more alien than Europa. Titan is the only moon in the solar system with a thick atmosphere, and its atmosphere is actually denser than Earth's at the surface, though composed primarily of nitrogen rather than oxygen. The orange haze that gives Titan its characteristic color comes from complex organic molecules called tholins, formed when solar ultraviolet radiation interacts with nitrogen and methane in the upper atmosphere. Titan has weather. It has clouds, rain, rivers, and lakes. But none of it involves water. On Titan, the liquid that cycles through the environment is methane. It rains liquid methane from the clouds, forms rivers of liquid methane that carve channels through the landscape, and collects in lakes and seas of liquid methane near the poles. The largest of these, Kraken Mare, is larger than the Caspian Sea on Earth. The landscape of Titan, beneath its thick haze, is shaped by the same kinds of processes that shape the landscape of Earth: erosion, deposition, and fluid flow, but with a completely different set of chemicals doing the work. Whether life could exist in Titan's methane lakes is a profound and open question. Life on Earth uses water as a solvent, and all known biochemistry is water-based. But the chemistry of life is ultimately about information storage and energy conversion, and some scientists have proposed theoretical frameworks for life that uses liquid methane as a solvent instead of water. Such life would need to be radically different from anything on Earth, and it would exist at temperatures of negative 179 degrees Celsius, which poses enormous biochemical challenges. No evidence for such life has been found, but Titan is a world so chemically rich and so complex that it demands further study. NASA's Dragonfly mission, a rotorcraft lander, is planned to launch in the late 2020s and travel to Titan, where it will fly between different surface sites, sampling the chemistry and searching for the building blocks of life. Dragonfly will be able to cover dozens of kilometers in a single flight, far more than any wheeled rover could travel on the surface, and will give scientists a sample of Titan's chemistry from multiple locations across a variety of terrain types. The mission represents a new approach to planetary exploration, using the thick atmosphere and low gravity of Titan as an advantage rather than a challenge. Saturn's moon Enceladus was not expected to be scientifically significant when the Cassini spacecraft first approached it. It was a small moon, only about 500 kilometers across, with a bright, icy surface. But in 2005, Cassini made one of the most surprising discoveries of the entire mission. Near Enceladus's south pole, where the surface is marked by 4 long, parallel fractures, informally called the Tiger Stripes, the spacecraft detected plumes of water vapor and ice, particles being ejected into space at roughly 1,500 kilometers per hour. Enceladus is actively venting material from its interior into space. Subsequent analysis of the plume material revealed not just water vapor and ice, but also complex organic molecules including hydrogen, silica nanoparticles consistent with hydrothermal activity on the seafloor, and molecular hydrogen, which indicates ongoing chemical reactions between hot water and rock, exactly the kind of environment associated with hydrothermal vents on Earth's ocean floor. The material from Enceladus's interior is being sprayed directly into space, where it can be studied without the need to drill through an ice shell. Cassini flew through the plumes 13 times, collecting samples and taking measurements, and the picture that emerged was of a small moon with a warm, chemically active ocean that may have the conditions to support life. Jupiter's moon, Io, is the most volcanically active body in the solar system. Io is caught in a gravitational tug-of-war between Jupiter and the other Galilean moons, primarily Europa and Ganymede, and the resulting tidal forces heat Io's interior so intensely that the Moon is covered in volcanoes. Over 400 active volcanic regions have been identified on Io's surface. Some of its volcanic plumes reach heights of 500 kilometers above the surface. The lava temperatures at some eruptions exceed 1700 degrees Celsius, hotter than any volcanic eruption on Earth. The surface of Io is constantly being resurfaced by volcanic activity, and the planet has no impact craters because any crater that forms is quickly buried under fresh lava flows. Io is a world that is being perpetually made and remade, constantly renewing itself through the endless churning of its volcanic interior. Neptune's moon Triton is one of the most unusual objects in the outer solar system. It is the only large moon in the solar system that orbits its planet in the retrograde direction, meaning it orbits in the opposite direction from Neptune's rotation. This strongly suggests that Triton did not form alongside Neptune. Instead, it was almost certainly a free-floating Kuiper Belt object that was captured by Neptune's gravity at some point in the distant past. The capture event would have been enormously energetic and would have dramatically altered the orbits of any moons that previously orbited Neptune. Triton's retrograde orbit means it is slowly losing energy and spiraling inward. In approximately 3.6 billion years, Triton will cross within Neptune's Roche limit, the distance at which Neptune's tidal forces will exceed the gravitational forces holding Triton together. At that point, Triton will be torn apart, and its material will form a ring system around Neptune far more extensive than the faint rings that exist today. Neptune will gain a spectacular ring system at the cost of its largest moon. Triton is also geologically active. Voyager 2 detected nitrogen geysers on its surface during the 1989 flyby, with plumes rising up to 8 kilometers into the thin atmosphere before being blown downwind by tens of kilometers. Triton's surface temperature is the coldest measured in the solar system, at negative 235 degrees Celsius, just 38 degrees above absolute zero. If you are still with us, and you are drifting between the planets and moons we have been describing, between sleep and wonder, then this video is doing exactly what it was made to do. If someone in your life loves space the way you do, share this with them. Let them fall asleep to the same stars. Now we turn from the worlds of the solar system to a different kind of object, the asteroids and comets that fill the spaces between the planets and occasionally make their presence known in dramatic fashion. The asteroid belt between Mars and Jupiter is home to millions of rocky and metallic objects, ranging in size from tiny pebbles to the dwarf planet Ceres, which is approximately 945 kilometers across. The asteroid belt is often depicted in science fiction as a densely packed maze of tumbling rocks, but the reality is far more empty. The total mass of all the objects in the asteroid belt is less than 4% of the mass of the Moon, and the average distance between objects large enough to be called asteroids is hundreds of thousands of kilometers. A spacecraft flying through the asteroid belt has never had to take any special action to avoid collision. The asteroid belt exists in its current form because Jupiter's gravity prevented the material in that region of the solar system from ever accumulating into a planet. Without Jupiter's gravitational disruption, the asteroids might have coalesced over billions of years into a rocky planet a little larger than Mars. Instead, they remain a fragmented population of remnants from the early solar system, and they are scientifically valuable precisely because of that. Asteroids are essentially the building blocks of planets that never got incorporated into one. They preserve a chemical and physical record of the conditions in the early solar system that has been altered or destroyed everywhere else, and missions to study them are essentially missions to study the raw materials from which the solar system was built. Some asteroids are predominantly metallic, composed largely of iron and nickel, and are thought to be the cores of larger bodies that were shattered by impacts early in the solar system's history. Others are rocky, composed of silicate minerals, and others are carbonaceous, rich in carbon compounds and water-bearing minerals, which makes them particularly interesting from an astrobiological perspective because they may carry some of the same organic chemistry that seeded the early Earth. The Japanese Hayabusa 2 mission returned samples from a carbonaceous asteroid called Ryugu in 2020, and analysis of those samples found amino acids, the building blocks of proteins, among dozens of organic compounds. This was not the first time amino acids had been found in meteorites, but the confirmed return of pristine asteroid material provided an unprecedented level of certainty about the extraterrestrial origin of these molecules. Not all asteroids stay in the asteroid belt. Gravitational interactions, particularly with Jupiter, can nudge asteroids into new orbits that bring them closer to the Sun. Some of these are called near-Earth asteroids, and a subset of those are classified as potentially hazardous because their orbits bring them within a certain distance of Earth's orbit. There are currently more than 2,300 known near-Earth asteroids, classified as potentially hazardous, meaning they are large enough and their orbits close enough to Earth's that a future impact cannot be entirely ruled out. The vast majority of these objects pose no immediate threat, but their existence is taken seriously enough that NASA maintains a dedicated Planetary Defense Coordination Office whose mission is to detect, track, and characterize near-Earth objects and to develop strategies for deflecting any that are found to be on a collision course. The most consequential impact in the last 66 million years was the strike that ended the reign of the non-avian dinosaurs. The Chicxulub impactor struck what is now the Yucatan Peninsula in Mexico approximately 66 million years ago. It was an asteroid or comet approximately 10 to 15 kilometers across, and the energy of its impact was roughly equivalent to 1 billion nuclear weapons detonating simultaneously. The impact vaporized rock instantaneously, threw enormous quantities of material into the atmosphere, triggered massive wildfires across the globe, and produced a global winter that lasted years as particulates blocked sunlight. Approximately 75% of all species on Earth went extinct in the aftermath. The thin layer of iridium found worldwide in rock strata at the 66 million year boundary is the geochemical fingerprint of that event. Iridium is rare in Earth's crust, but common in asteroids, and its presence in rock layers across the world is the global signature of an impact that reshaped the history of life on this planet. The hypothesis that an asteroid impact caused the end Cretaceous extinction was first proposed by Luis Alvarez and his son Walter Alvarez in 1980, based on their discovery of this iridium layer. It was initially met with deep skepticism by the geological community, but the subsequent discovery of the Chicxulub crater and the accumulation of additional evidence eventually made it one of the most thoroughly confirmed hypotheses in the history of Earth science. In 2022, NASA demonstrated for the first time that human beings can actually change the orbit of an asteroid. The Double Asteroid Redirection Test, or DART mission, deliberately crashed a spacecraft into a small asteroid called Dimorphos, a moon of the larger asteroid Didymos, to see if the impact could alter its orbit. The spacecraft hit its target on September 26, 2022, and subsequent observations confirmed that Dimorphos's orbital period around Didymos had changed by 32 minutes, significantly more than scientists had predicted. The mission was a proof of concept for planetary defense. If we detect a dangerous asteroid far enough in advance, we have a method to deflect it. Comets are different from asteroids in composition, but similar in one crucial respect. They are leftovers from the formation of the solar system. While most asteroids are rocky or metallic, comets are composed of ice, dust, and rocky material, often described as dirty snowballs. They originate primarily in the Kuiper Belt and the Oort cloud, and they develop their spectacular tails only when they venture into the inner solar system, close enough to the sun that solar radiation and the solar wind heat the icy nucleus and cause it to sublimate, releasing gas and dust that form the glowing coma and the long tails that make comets such a striking sight. A comet typically develops two distinct tails when it approaches the Sun. The dust tail curves gently behind the comet along its orbital path, reflecting sunlight and appearing white or yellowish. The ion tail, which is made of electrically charged gas blown directly away from the Sun by the solar wind, always points directly away from the Sun regardless of the comet's direction of travel. The two tails spread apart at an angle, giving comets their characteristic appearance in historical depictions and in photographs taken by modern telescopes. Halley's Comet is the most famous of all comets. It has been recorded by human observers for at least 2,000 years, with documented sightings going back to 240 BC. Its appearance in 1066 was recorded on the Bayeux Tapestry, the famous embroidered narrative of the Norman conquest of England, where it appears above a group of pointing men clearly terrified by its presence. Edmund Halley, the British astronomer, was the first to calculate that several comets observed in different years were actually the same comet returning, and he correctly predicted its next appearance in 1758, 16 years after his own death. Halley's Comet returns approximately every 75 to 76 years. Its most recent visit was in 1986, when a fleet of spacecraft, including the European Space Agency's Giotto probe, made close flybys and returned the first detailed images of a comet's nucleus. The nucleus of Halley's Comet turned out to be roughly 15 kilometers long and 8 kilometers wide, irregularly shaped, very dark, and highly active. It will next be visible from Earth in 2061. Every star you see in the night sky is a sun. Some are similar to ours, many are very different, and all of them are passing through stages of a life cycle that begins in a cloud of gas and dust and ends in ways that depend on how much mass the star contains. Understanding the life cycle of stars is understanding the history of the universe, because stars are the engines that manufacture the elements, distribute them through space, and create the conditions necessary for planets, chemistry, and ultimately life. Stars form in regions of space, called stellar nurseries, or nebulae, where dense clouds of gas and dust have been compressed enough by gravity to begin collapsing. The process is the same one that formed our Sun, but it happens repeatedly and simultaneously across these vast clouds, giving birth to clusters of stars, rather than single stars in isolation. The clouds from which stars form are extraordinarily vast. The Eagle Nebula, home to the famous Pillars of Creation, photographed by the Hubble Space Telescope in 1995, spans approximately 70 light-years across. Within this cloud, multiple generations of stars have formed over millions of years, with the energetic radiation from massive young stars simultaneously sculpting the surrounding gas and triggering the collapse of nearby regions to form even more stars. Some of the most famous images in the history of astronomy capture these nurseries in action. The Pillars of Creation, photographed by the Hubble Space Telescope in 1995, and again in stunning detail by the James Webb Space Telescope in 2022, shows columns of cool gas and dust rising from the Eagle Nebula, with new stars forming at the tips of the pillars, where the density is highest. The pillars themselves are several light-years tall, extending into space like enormous fingers of dark gas, backlit by the hot, young stars surrounding them. There is a remarkable detail about the Pillars of Creation that illustrates one of the most disorienting aspects of looking at the universe. The pillars we are seeing in those photographs are the pillars as they were approximately 6,500 years ago, when the light we are looking at today left them. Some scientists believe that a supernova exploded near the pillars about 6,000 years ago, and that the resulting shockwave has already destroyed them. But the light from that destruction has not reached us yet. When you look at the Pillars of Creation today, You may be looking at an object that no longer exists. Once a protostar accumulates enough mass and its core temperature reaches approximately 10 million degrees Celsius, nuclear fusion ignites, and the star enters what is called the main sequence phase of its life. This is the long, stable phase during which the star burns hydrogen in its core, converting it to helium and releasing energy. The length of the main sequence phase depends almost entirely on mass. More massive stars burn hotter and faster, consuming their fuel in millions of years. Less massive stars burn cooler and more slowly, lasting for tens or even hundreds of billions of years. Our Sun is expected to remain on the main sequence for approximately 10 billion years total. It is currently about 4.6 billion years into that phase, roughly halfway through its stable life. The most massive stars, those with 30 or more times the mass of our Sun, live extraordinarily fast and brief lives by stellar standards. They burn so intensely that they exhaust their hydrogen fuel in just a few million years, compared to the 10 billion years available to the Sun. These massive stars are among the brightest objects in the galaxy, outshining the Sun by factors of 100,000 or more, but they are also among the rarest, because they consume themselves so rapidly. The most massive stars end their lives in spectacular supernovae that can briefly outshine entire galaxies and leave behind either neutron stars or black holes. They are the universe's most prolific manufacturers of heavy elements, forging carbon, oxygen, silicon, iron, and everything else in their brief, brilliant lives. When the hydrogen in the core of a Sun-like star is exhausted, the core begins to contract under gravity, while the outer layers expand dramatically and the star transforms into a red giant. The red giant phase represents the Sun's old age. As a red giant, the Sun will be large enough to engulf the inner planets. The surface temperature will drop, giving it a reddish color compared to its current yellow-white. This phase will last approximately 1 billion years, after which the Sun will shed its outer layers in a glowing cloud of gas called a planetary nebula, leaving behind a small, incredibly dense remnant called a white dwarf. Planetary nebulae are among the most visually spectacular objects in the night sky. Despite the name, they have nothing to do with planets. The name dates from the era of early telescopy, when astronomers noticed that these objects appeared round and planetary-like through their instruments. In reality, a planetary nebula is the expelled outer envelope of a dying star, illuminated and ionized by the ultraviolet radiation from the hot white dwarf at its center. The Ring Nebula in the constellation Lyra, the Cat's Eye Nebula in Draco, and the Helix Nebula in Aquarius are among the most photographed and studied examples. Each one represents a sun that has died, leaving behind a beautiful, expanding shell of gas that will eventually disperse into the interstellar medium. A white dwarf is essentially the naked core of a dead star, roughly the size of Earth, but containing the full mass of the original star. It has no fusion reactions occurring within it. It simply radiates away the heat accumulated over billions of years of fusion. White dwarfs cool very slowly. The oldest white dwarfs known are perhaps 11 to 12 billion years old and have cooled to temperatures of just a few thousand degrees. Over time, they will continue to cool toward absolute zero, eventually becoming what are called black dwarfs, completely dark, cold remnants. But the universe has not existed long enough for any black dwarfs to have formed yet. The cooling timescale is so long that even the oldest white dwarfs in the universe are still glowing. Black dwarfs are objects that are still in the future, waiting billions of trillions of years from now to become real. For stars significantly more massive than our Sun, the ending is far more dramatic. A star with more than 8 times the Sun's mass will not end as a white dwarf. Instead, when its core runs out of nuclear fuel, the core collapses catastrophically in a fraction of a second, and the outer layers come crashing inward, before rebounding in a colossal explosion called a supernova. A supernova at its peak can briefly outshine an entire galaxy, billions of stars together, from a single exploding point. The explosion disperses the star's outer layers, including all the heavy elements forged in its core throughout its life, into the surrounding space. These elements seed the interstellar medium and will eventually become incorporated into new molecular clouds, new stars, new planets, and new life. Supernovae are the primary mechanism by which the universe distributes heavy elements, and every element heavier than hydrogen and helium that exists in your body, in the earth beneath your feet, in the metals and minerals and gases around you, was created in a star and distributed by a stellar explosion. The iron in your blood, the calcium in your bones, the oxygen in every breath you take, all of it was forged in the core of a star that no longer exists, scattered by its death into the galaxy, gathered up by our solar system 4.6 billion years ago, and incorporated into the planet, and eventually the living things that grew from it. Every element heavier than iron in the universe was forged in something even more extreme than a supernova. Elements like gold, platinum, uranium, and dozens of others are too heavy to be produced in the steady nuclear burning of a star's core. They require conditions of extraordinary temperature, density, and neutron flux that are only achieved in the final moments of a supernova explosion or, as scientists confirmed definitively in 2017, in the collision of two neutron stars. On August 17, 2017, gravitational wave detectors at LIGO in the United States and Virgo in Italy detected a signal called GW170817, caused by two neutron stars spiraling together and merging approximately 130 million light-years away. Within seconds of the gravitational wave detection, gamma-ray telescopes detected a burst of gamma radiation from the same location, the first time a gravitational wave event had been matched to an electromagnetic signal of any kind. Over the following days and weeks, telescopes around the world observed the aftermath of the collision, called a kilonova, and detected clear spectroscopic signatures of heavy elements being created in real time. The analysis confirmed that the merger had produced enormous quantities of heavy elements, including an estimated 10 Earth masses of gold, and similarly large amounts of platinum, uranium, and other heavy metals. Every heavy element that has ever been mined, every gold coin, every platinum catalyst, every uranium fuel rod, came from events like this one. Two dead stars, the cores of ancient suns, spiraling together over billions of years and merging in a burst of energy detectable across 100 million light-years of space. The gold in your jewelry is older than the solar system. It arrived on Earth in the asteroids and comets that bombarded the young Earth 4 billion years ago. It has been here ever since, waiting to be dug out of the ground, shaped, polished, and worn, entirely unaware of the extraordinary journey it took to get there. SN 1987A was a supernova that exploded in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, approximately 160,000 light-years away. When the light from the explosion reached Earth on February 23, 1987, it was the first supernova visible to the naked eye since the one observed by Johannes Kepler in 1604. Astronomers around the world turned their telescopes toward it and recorded everything they could. For the first time in the history of astronomy, scientists had advance notice of a nearby supernova through the detection of neutrinos, ghostly particles that escaped from the collapsing core before the explosion itself, giving physicists a few hours of warning before the visible light arrived. The neutrino burst from SN 1987A, detected by underground detectors in Japan, the United States, and the Soviet Union simultaneously, was the first direct detection of neutrinos from a source outside the solar system, and it confirmed the basic theoretical picture of how massive stars collapse to form neutron stars. In the decades since, the remnant of SN 1987A has been expanding and brightening, and astronomers believe a neutron star should have formed at its center. Recent James Webb Space Telescope observations have found evidence of the presence of this neutron star, though confirming it directly remains challenging due to the dense surrounding gas and dust from the explosion itself. Type 1a supernovae, which occur in binary star systems when a white dwarf accumulates enough mass from a companion star to trigger a runaway nuclear explosion, are particularly important in cosmology because they always reach approximately the same intrinsic brightness, making them useful as standard candles for measuring distances across cosmic scales. It was the use of Type 1a supernovae as distance indicators that led to the discovery in 1998 that the universe's expansion is accelerating, one of the most surprising and consequential discoveries in the history of cosmology. We will return to this discovery and its implications shortly. When a star between roughly 8 and 20 times the mass of the Sun reaches the end of its life and its core collapses, the result is a neutron star, one of the densest objects in the known universe. To understand what a neutron star is, consider first what it means for matter to be compressed to neutron density. An atomic nucleus is roughly 100,000 times smaller than an atom. If you were to compress all the empty space out of an atom and leave only the nucleus, you would have something approaching the density of a neutron star. A neutron star packs the mass of 1.5 to 2 suns into a sphere approximately 20 kilometers across, roughly the size of a city. The density of a neutron star is so extreme that a single teaspoon of its material would weigh approximately 4 billion tons on Earth. The surface gravity is about 200 billion times Earth's surface gravity. If you dropped an object onto a neutron star from a height of 1 meter, it would hit the surface at roughly 2 million kilometers per hour. The neutron star's crust is the strongest material known to exist, approximately 10 billion times stronger than steel. And beneath the crust, the interior of a neutron star may contain forms of matter that have no equivalent anywhere else in the observable universe, potentially exotic states like quark matter or strange matter, which are the subject of intense theoretical and observational research. Neutron stars rotate. They begin rotating when the collapsing stellar core conserves its angular momentum during the supernova, in the same way that a spinning ice skater speeds up when pulling in their arms. The initial stellar core might have been rotating once every few days. When it collapses from a sphere hundreds of thousands of kilometers across to a sphere 20 kilometers across, the conservation of angular momentum causes it to spin hundreds of times per second. As the neutron star emits beams of electromagnetic radiation from its magnetic poles, and as those poles are often not aligned with the rotation axis, the beams sweep around like the beam of a lighthouse. If one of those beams happens to point toward Earth, we detect a regular pulse of radiation each time the beam sweeps past, and we call the object a pulsar. Pulsars are among the most precise timekeepers in nature. The most stable pulsars maintain their period to within a nanosecond per day, rivaling the precision of the best atomic clocks on Earth. They have been used to test the predictions of general relativity with extraordinary precision, and they have been proposed as navigational beacons for future deep space missions. Pulsar timing arrays, networks of precisely timed pulsars distributed across the sky, are being used to detect gravitational waves with frequencies too low for ground-based detectors like LIGO to detect, opening a new window on some of the universe's most extreme events. In 1967, a young Cambridge University graduate student named Jocelyn Bell Burnell was working on a newly built radio telescope, scanning the sky for quasars. She noticed a strange, repeating signal in the data, a pulse that arrived with extraordinary regularity, every 1.337 seconds. The signal was so regular, so precise, and so unlike any known natural phenomenon that the Cambridge team initially labeled it LGM-1 for Little Green Men 1. They genuinely considered, briefly, the possibility that it was a signal from an extraterrestrial intelligence. It was only after further analysis revealed that the signal was Doppler shifted in a way consistent with Earth's orbit around the Sun, and after 3 more similar sources were found in different parts of the sky, that the team concluded they had discovered a new class of natural object. The first pulsar had been found. Jocelyn Bell Burnell did not share in the Nobel Prize that was subsequently awarded for the discovery of pulsars. The prize went to her supervisor, Anthony Hewish, and to radio astronomer Martin Ryle. Bell Burnell was not included. The omission has been widely criticized as one of the most significant oversights in the history of the Nobel Prize, and Bell Burnell herself has handled the controversy with remarkable grace, saying in interviews that she does not feel particularly bad about it. She has since received numerous other honors, and in 2018 was awarded the Special Breakthrough Prize in Fundamental Physics, which carries a prize of $3 million. She donated the entire amount to fund scholarships for underrepresented students in physics. Magnetas are a specialized class of neutron star with magnetic fields that are trillions of times stronger than Earth's magnetic field and thousands of times stronger than those of typical neutron stars. The magnetic field of a magnetar is the strongest sustained magnetic field in the known universe. These extraordinary magnetic fields give magnetars their most distinctive property: intense bursts of X-ray and gamma-ray radiation, sometimes called starquakes, caused by stress fractures in the magnetar's ultradense crust as the magnetic field shifts. In December 2004, a magnetar called SGR 1806-20, located approximately 50,000 light-years away, released a burst of energy in approximately 0.2 of a second that exceeded the total energy output of the Sun over the preceding 250,000 years. The burst was so powerful that it ionized Earth's upper atmosphere and affected the readings of space-based detectors designed to observe gamma-ray sources across the entire universe. The magnetar was 50,000 light-years away, and it still measurably affected our planet. If a magnetar of comparable activity were located within a few light-years of Earth, it could strip away the ozone layer and cause a mass extinction. Now we come to the objects that have perhaps captured the human imagination more than any other astronomical phenomenon. Objects that were once purely theoretical, mathematical constructions that physicists were not sure had any physical reality, and that are now confirmed to exist throughout the universe in vast numbers: black holes. A black hole forms when a massive star's core collapses, and no known force is sufficient to stop the collapse. The pressure and density at the center increase without limit, forming what is mathematically described as a singularity, a point of infinite density. Surrounding the singularity is the event horizon, the boundary beyond which nothing, not matter, not light, not any signal of any kind, can escape. The event horizon is not a physical surface. There is nothing special at the event horizon in terms of local physics. An astronaut falling through it would feel nothing unusual in the moment of crossing. But the event horizon is a point of no return. Once crossed, all paths, all trajectories led inward. The gravitational field near a black hole is strong enough to cause significant distortions of space and time. Time runs slower near a massive object, a prediction of Einstein's general relativity that has been experimentally confirmed in many contexts. Near a black hole, this effect is extreme. An observer watching from a safe distance would see an object falling toward the event horizon appear to slow down and freeze at the horizon, growing dimmer and dimmer as the light from it is increasingly red-shifted, never quite seeming to cross. From the perspective of the infalling object, the crossing happens in finite time and with no particular drama. What would happen to a human being who fell into a stellar mass black hole is described by the evocative term spaghettification. The gravitational field at the event horizon of a stellar mass black hole is so strong that the tidal forces, the difference in gravity between your feet and your head if you fell in feet first, would be sufficient to stretch your body into a long, thin strand of matter before you crossed the horizon. However, for a supermassive black hole, one containing millions or billions of solar masses, the event horizon is so large that the tidal forces at the horizon are actually quite gentle. An astronaut falling into the supermassive black hole at the center of the Milky Way would not be spaghettified at the horizon. They would cross it smoothly, unaware that they had passed the point of no return. It would only be later, as they fell deeper inward, that the tidal forces would become fatal. There are primarily three recognized types of black holes. Stellar black holes form from the collapse of massive individual stars and typically have masses ranging from a few to several tens of solar masses. They are the most common type, distributed throughout galaxies wherever massive stars have lived and died. Supermassive black holes reside at the centers of most large galaxies, including our own Milky Way, and contain masses equivalent to millions or even billions of suns. Their formation mechanism is still debated, with leading theories involving the merger of smaller black holes over cosmic timescales, or the direct collapse of enormous gas clouds in the early universe. Intermediate mass black holes, with masses between a few hundred and a few 100,000 solar masses, are a more recently identified class that fills the gap between stellar and supermassive black holes, and their existence has been confirmed in a small number of cases. The Event Horizon Telescope project represents one of the most extraordinary feats of observational astronomy in history. To image a black hole directly, specifically to image the shadow of its event horizon against the glow of surrounding matter, requires an effective telescope with a resolution of roughly 20 microarcseconds. No single telescope on Earth can achieve this. The Event Horizon Telescope solved this problem by linking radio telescopes across the globe, from Hawaii to Spain, from Chile to Antarctica, creating an effective telescope aperture the size of the entire Earth, and exploiting the principle of very long baseline interferometry. In April 2017, the array of telescopes all pointed, simultaneously at the same target, a supermassive black hole called M87 star at the center of the galaxy Messier 87, approximately 55 million light-years away. The data collected was so massive that it could not be transmitted electronically. Hard drives were physically flown from the telescope sites to central processing facilities in Massachusetts and Germany. The data processing took nearly 2 years. In April 2019, the Event Horizon Telescope team released the first image of a black hole ever produced, a bright ring of glowing gas surrounding a dark central region, the shadow of the event horizon against the accretion disk. It was a milestone comparable to the first photograph of Earth from space. In May 2022, the Event Horizon Telescope team released the first image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, approximately 26,000 light-years away. Imaging SGR A star was technically more challenging than imaging M87 star, because SGR A star is much smaller and its surrounding material orbits it much faster, causing the image to change on timescales of minutes rather than days. The resulting image was nonetheless extraordinary, showing the same characteristic bright ring around a dark central shadow. SGR A star contains approximately 4 million times the mass of our Sun. It sits at the gravitational center of the Milky Way. Every star in our galaxy, including our Sun, orbits around it. Stephen Hawking predicted in 1974 that black holes are not completely black. Quantum mechanical effects near the event horizon should cause black holes to slowly radiate energy, a process now called Hawking radiation. For a stellar mass black hole, the rate of evaporation is so slow that the black hole will take approximately 10 to the power of 67 years to completely evaporate. A number so large that it dwarfs the current age of the universe by an almost incomprehensible margin. But the physics predicts it will happen eventually, and when the last of the mass is gone, the black hole will end in a final burst of radiation. Hawking radiation has never been directly observed because the effect is far too faint to detect with current instruments, but the theoretical derivation is considered one of the most important results in theoretical physics, bridging general relativity and quantum mechanics in a way that has deep implications for our understanding of both. The Milky Way is our home galaxy. We are inside it, which means we cannot step outside and look at it the way we can look at other galaxies. Everything we know about its structure has been inferred from observations made from within, a challenge not unlike trying to draw a map of a city you have never left. Despite this limitation, astronomers have been able to piece together a remarkably detailed picture of the Milky Way's structure using radio telescopes, infrared observations that penetrate the dust clouds, obscuring the visible light view, and surveys of stellar positions and motions. The Milky Way is a barred spiral galaxy. It has a central bar of stars at its core and spiral arms curving outward from the ends of the bar. The entire disk is approximately 100,000 light-years across and about 1,000 light-years thick, though the disk is somewhat warped and not perfectly flat. Our Sun is located about 26,000 light-years from the galactic center, roughly two-thirds of the way out toward the edge, in a region called the Orion Arm, or Orion Spur, a minor arm between two of the major spiral arms. The Milky Way contains somewhere between 200 billion and 400 billion stars. On a clear, dark night, far from city lights, you can see a faint band of light stretching across the sky, the combined glow of billions of stars in the plane of the galaxy's disk, too distant to be resolved individually. That band is the edge-on view of our galaxy's disk. We are inside it, looking along its length. The name Milky Way comes from the Latin Via Lactea, the Milky Road, which itself derives from the Greek galaxias, referring to the pale, milky appearance of the band of stars visible on a clear night. The word galaxy comes from the same root. Our solar system orbits the center of the Milky Way at approximately 828,000 kilometers per hour. A complete orbit, sometimes called a cosmic year or a galactic year, takes between 225 and 250 million Earth years. The last time our solar system was in the same position in the galaxy relative to the center, the Triassic period was just beginning on Earth. The first dinosaurs had not yet evolved. The continents were arranged differently, with most of Earth's landmasses still joined in the supercontinent Pangaea. We have orbited the galaxy approximately 20 times since the solar system formed. At the center of the Milky Way sits Sagittarius, a star, the supermassive black hole we have already visited. But the galactic center is not just a black hole, it is one of the most extreme environments in the galaxy, densely packed with stars, many of which orbit SGR-A star at high speeds on elliptical orbits. The star S2, one of the closest known to SGR-A star, has an orbital period of approximately 16 years and reaches speeds of nearly 3% of the speed of light at its closest approach to the black hole. Observations of S2 and other stars in the galactic center provided the most compelling early evidence that SGR-A star is indeed a supermassive black hole rather than any other kind of dense object. The visible disk of the Milky Way is surrounded by a vast, roughly spherical halo of older stars, globular clusters, and extending far beyond the visible disk, a massive invisible structure called the dark matter halo. The dark matter halo is estimated to contain roughly 10 times as much mass as all the visible stars, gas, and dust in the galaxy combined. We know it is there because, without it, the outer stars of the Milky Way would not orbit the center at the speeds they do. They are orbiting too fast for the visible mass alone to hold them. Something else, something we cannot see, is providing additional gravitational pull. The Milky Way is not alone in space. It belongs to a collection of galaxies called the Local Group, which contains more than 50 known members spread across a volume approximately 10 million light-years across. The two largest members of the Local Group are the Milky Way and the Andromeda Galaxy, also known as Messier 31. Andromeda is a spiral galaxy like our own, slightly larger, containing over 1 trillion stars compared to the Milky Way's estimated 2 to 400 billion. It is the most distant object visible to the naked eye from Earth, appearing as a faint smear of light in the constellation Andromeda on a clear, dark night. The light you are seeing from Andromeda left its source approximately 2.5 million years ago. When that light began its journey, the first members of the genus Homo were walking the African savanna. Andromeda and the Milky Way are approaching each other. Pulled together by mutual gravitational attraction, the two galaxies are converging at approximately 110 kilometers per second. In approximately 4.5 billion years, they will collide. The collision will not be like two solid objects crashing into each other. The distances between individual stars are so vast that direct stellar collisions will be vanishingly rare. Instead, the two galaxies will interpenetrate, with stars streaming past each other at enormous speeds, while gravitational forces distort and reshape both galaxies' structures. The spiral arms will be disrupted. Vast tidal tails of stars will be flung into intergalactic space. New bursts of star formation will be triggered as clouds of gas are compressed by the interaction. The collision and merger will likely take approximately 2 billion years to complete, going through several passes before the two galaxies finally merge into a single elliptical galaxy. The two supermassive black holes at their respective centers will gradually spiral together and eventually merge, releasing an enormous burst of gravitational waves in the process. The combined galaxy formed from the merger has been given a provisional name, Milkomeda, or sometimes Milkdromeda. It is a future our Sun will witness, in the sense that the Sun will still exist, though the solar system as we know it may be in an entirely different location within the merged galaxy than it occupies today. Beyond the Local Group lies the Virgo supercluster, a vast collection of galaxy groups and clusters of which the Local Group is a minor, outlying member. The Virgo supercluster is approximately 110 million light-years across and contains roughly 100 galaxy groups and clusters. And even the Virgo supercluster is embedded within an even larger structure called Laniakea, the supercluster mapped in 2014, spanning approximately 500 million light-years and containing the mass of 100 million billion suns with approximately 100,000 galaxies. Pointing toward the heart of Laniakea, and indeed toward a region beyond it, is a mysterious gravitational anomaly known as the Great Attractor. Something in the direction of the constellation Centaurus is pulling our entire local universe toward it, drawing the Milky Way, Andromeda, and hundreds of other galaxies at speeds of approximately 1,400,000 kilometers per hour. For decades, astronomers could not see what was causing this attraction because it lies in the zone of avoidance, a region of sky obscured by the dust and stars of the Milky Way's own disk. Observations in wavelengths that penetrate dust have now revealed a concentration of galaxies called the Norma cluster, embedded in an even larger supercluster called the Shapley concentration, in the direction of the attraction. Whether this accounts for all of the observed gravitational pull is still debated. The universe is composed of 4 main ingredients: the ordinary matter that makes up stars, planets, gas, dust, and every living thing constitutes approximately 5% of the total. The remaining 95% is divided between 2 things we cannot see, cannot touch, and have never directly detected: dark matter, which makes up approximately 27%, and dark energy, which makes up approximately 68%. The universe is, in the most literal sense, mostly made of things we do not understand. Dark matter was first seriously proposed as a concept in the 1930s, when the Swiss astronomer Fritz Zwicky measured the velocities of galaxies in the Coma cluster and found that they were moving too fast to be held together by the visible mass of the cluster alone. He proposed that there must be additional, invisible mass providing the extra gravitational pull. For decades, the idea was largely ignored. Then, in the 1970s, the American astronomer Vera Rubin and her colleague Kent Ford measured the rotation curves of spiral galaxies, mapping how the orbital speeds of stars change with their distance from the galaxy's center. If galaxies contained only the visible matter we could observe, the orbital speeds of stars should decrease with distance from the center, just as the outer planets of our solar system orbit the Sun more slowly than the inner ones. But that is not what Rubin and Ford found. Across galaxy after galaxy, the orbital speeds remained roughly constant out to the edge of the visible disk, and in some cases continued at the same speed beyond the visible stars entirely. The only explanation consistent with the laws of gravity is that the galaxies are embedded in vast halos of invisible mass, with the total mass of the halo being several times larger than the visible mass of the galaxy. This invisible mass is dark matter. Vera Rubin spent years presenting this evidence to the astronomical community, and years being met with skepticism. The resistance she faced was not purely scientific. She was one of the first women to observe at the Palomar Observatory in California, and she navigated throughout her career in an environment that was deeply unwelcoming to women in science. The data eventually became undeniable. By the time of her death in 2016, the existence of dark matter was considered one of the most well-established observational facts in cosmology. She never received a Nobel Prize for what is arguably one of the most significant discoveries in the history of astronomy. What dark matter actually is remains one of the deepest unsolved problems in physics. It does not emit, absorb, or reflect light. It does not interact with ordinary matter through any of the fundamental forces except gravity. It passes through ordinary matter without any detectable effect. The leading candidates include weakly interacting massive particles, known as WIMPs, hypothetical particles with masses in the range of 10 to 1,000 times the mass of a proton that interact with ordinary matter only through gravity and the weak nuclear force. Axions, hypothetical very light particles, originally proposed to solve a different problem in particle physics, are another leading candidate. Despite decades of searching with the world's most sensitive detectors deep underground in abandoned mines and tunnels designed to shield out cosmic ray interference, none of these particles have been detected directly. Dark matter is the dominant ingredient in the universe, and we do not know what it is. Dark energy is an even deeper mystery, and its discovery ranks among the most surprising results in the history of science. In 1998, two independent teams of astronomers were using Type 1a supernovae as distance markers to map the expansion history of the universe. Both teams expected to find that the universe's expansion was slowing down over time, decelerated by the mutual gravitational attraction of all the matter within it. Instead, they found the opposite. The universe's expansion is accelerating. Distant supernovae were dimmer than expected, meaning they were farther away than they should have been if the universe had been decelerating. The universe is not just expanding. It is expanding faster and faster as time goes on, driven by something that acts like a repulsive energy density permeating all of space. This something is what we now call dark energy. Einstein had actually included a similar term in his equations of general relativity as early as 1917, a cosmological constant that he had introduced to allow for a static universe. He later called it his greatest blunder when Edwin Hubble's observations confirmed that the universe was expanding. But the 1998 supernova results revealed that the cosmological constant, or something very much like it, is real after all, and it is driving the accelerating expansion we observe. The discovery earned the 2011 Nobel Prize in Physics for Saul Perlmutter, Brian Schmidt, and Adam Rees. The implications of dark energy are profound. If the expansion continues to accelerate indefinitely, the universe will become increasingly sparse and cold as galaxies are carried apart by the expanding space between them. In the very far future, the local group will be all that remains visible to us from Earth, with all other galaxies having receded beyond the cosmological horizon. The universe will become a colder, darker, more isolated place with the passage of time. Before any of this existed, there was nothing. And then, in a way that defies the ordinary meaning of the word when, there was everything. The Big Bang is the name we give to the beginning, but the name is somewhat misleading. It implies an explosion in space, a detonation at a specific point that sent matter flying outward. This is not what happened. The Big Bang was not an explosion in space. It was an expansion of space itself, and it happened everywhere simultaneously because everywhere was at a single point. There was no center. There was no surrounding void for the universe to expand into. Space itself did not exist before the Big Bang, and it came into existence as part of the event itself. This is genuinely difficult to visualize because our intuitions about space and time are built on our experience of a universe that already exists. But the mathematics of general relativity allows us to trace the universe's expansion backward in time to earlier and earlier moments when the universe was smaller, hotter, and denser. As we trace backward, we reach a point where our current laws of physics break down, where quantum effects become dominant, where the concepts of space and time themselves become unreliable guides. This is the Planck epoch, the first 10 to the power of -43 seconds, and it represents the boundary of what our current physical theories can address. What we can say with confidence begins a fraction of a second later. In the first 3 minutes after the Big Bang, the universe cooled from an initial temperature of trillions of degrees to about 1 billion degrees, and in that cooling, the fundamental building blocks of ordinary matter assembled. Protons and neutrons formed first, followed by the fusion of protons and neutrons into the nuclei of the lightest elements, primarily hydrogen and helium, with traces of lithium. This process, called Big Bang nucleosynthesis, determined the basic chemical composition of the early universe. Approximately 75% hydrogen and 25% helium by mass, with almost nothing heavier. Everything heavier than helium that exists in the universe today was made later, in stars. For the next 380,000 years after the Big Bang, the universe remained opaque. It was a plasma of free protons, electrons, and photons, all in constant interaction, with photons unable to travel more than a tiny distance before being absorbed and re-emitted. The universe was a glowing fog. Then, as the universe expanded and cooled to approximately 3,000 degrees, electrons and protons combined to form neutral hydrogen atoms for the first time in an event called recombination. The universe became transparent, and light was free to travel. The photons that were released at this moment have been traveling ever since, cooling as the universe expanded, and they are still detectable today as the cosmic microwave background radiation, a faint glow of microwave radiation filling the entire sky uniformly. The oldest light in the universe, a snapshot of what the universe looked like 380,000 years after its birth. The cosmic microwave background was discovered accidentally in 1965 by two Bell Labs engineers named Arno Penzias and Robert Wilson. They were working with a highly sensitive radio antenna in New Jersey and were troubled by a persistent, uniform noise in their equipment that they could not eliminate. They checked everything. They removed pigeon droppings from the antenna. They ruled out interference from nearby cities and from nuclear weapons tests. The noise remained, equally strong in every direction, persistent at every hour of the day and every month of the year. Eventually, they contacted Robert Dicke at Princeton University, who was in the process of building a detector specifically to look for this signal. Dicke recognized immediately what Penzias and Wilson had found. They had discovered the echo of the Big Bang. Penzias and Wilson received the Nobel Prize in Physics in 1978. After recombination, the universe entered a period called the Dark Ages. There were no stars yet, no galaxies, no sources of light. The universe was filled with clouds of neutral hydrogen and helium, slowly clumping under the influence of gravity, drawn together by slight variations in density that had been seeded in the early universe during an extraordinary process called cosmic inflation. Cosmic inflation was a period of exponential expansion that occurred in the first tiny fraction of a second after the Big Bang, before the universe had cooled enough for ordinary matter to exist in its current form. During inflation, the universe expanded by a factor of at least 10 to the power of 26, in less than 10 to the power of negative 32 seconds. This expansion was faster than the speed of light. This does not violate relativity because it is space itself that was expanding, not objects moving through space. Inflation smoothed out the universe on large scales, explaining why the cosmic microwave background is so remarkably uniform in temperature across the entire sky. But it also stretched microscopic quantum fluctuations to macroscopic scales, imprinting tiny variations in density across the universe. These variations became the seeds of everything that came later: the galaxies, the galaxy clusters, the cosmic web of filaments and voids that describes the large-scale structure of the universe today. The first stars formed approximately 100 to 200 million years after the Big Bang, ending the Dark Ages by flooding the universe with ultraviolet radiation that ionized the surrounding hydrogen. These first stars were very different from the stars we see today. They were composed almost entirely of hydrogen and helium, with essentially no heavier elements, because no heavier elements had yet been made. Without heavier elements, the gas clouds that formed these first stars could not cool as efficiently during collapse, and the stars that formed were consequently much more massive than typical stars today, potentially hundreds of times the mass of the Sun. They lived fast and died young, burning through their fuel in just a few million years before ending in supernovae that scattered the first heavy elements into the universe. The second generation of stars formed from gas enriched by these first stellar explosions, and each subsequent generation has been enriched by all the generations before it. We have spent much of this journey looking at the structure of the universe and the physics of its components. Now we turn to perhaps the most compelling question of all. Is any of what we have described also happening elsewhere? Are there other planets, other suns with worlds of their own? And on any of those worlds, is there anything looking back at us? For most of human history, the existence of planets around other stars was a matter of philosophical speculation. We could not observe them directly. The first confirmed detection of a planet orbiting another sun, called an exoplanet, came in 1992, when two planets were found orbiting a pulsar, and the first planet around a sun-like star was confirmed in 1995 by the Swiss astronomers Michel Mayer and Didier Queloz. That planet, 51 Pegasi b, was a gas giant about half the mass of Jupiter, orbiting its star in just 4 Earth days, at a distance so close that its year was shorter than an Earth week. Mayer and Queloz received the Nobel Prize in Physics for this discovery in 2019. In the years since 1995, the field of exoplanet science has transformed. The Kepler Space Telescope, launched by NASA in 2009 and operational until 2018, was designed with a single purpose: to stare continuously at a patch of the sky containing approximately 150,000 stars and watch for the tiny dimming that occurs when a planet passes in front of its host star. This method, called the transit method, allowed Kepler to detect planets even when they were far too small and too faint to be imaged directly. During its mission, Kepler confirmed the existence of more than 2,600 exoplanets and identified thousands more candidates awaiting confirmation. The most profound statistical result from Kepler was that planets are not rare. They appear to be ubiquitous. Based on Kepler data, astronomers estimate that most stars in the Milky Way host at least one planet, and that there are tens of billions of Earth-sized planets in the habitable zones of their stars in our galaxy alone. The habitable zone is the range of orbital distances from a star at which liquid water could potentially exist on a planet's surface, given the right atmospheric conditions. It is sometimes called the Goldilocks zone, not too hot and not too cold. The TRAPPIST-1 system, located approximately 39 light-years from Earth, is one of the most remarkable exoplanetary systems known. TRAPPIST-1 is an ultra-cool dwarf star, much smaller and cooler than the Sun, and around it orbit 7 Earth-sized planets. 3 of these planets, designated E, F, and G, lie within the star's habitable zone and receive amounts of stellar energy comparable to what Venus, Earth, and Mars receive from our Sun. The discovery of the TRAPPIST-1 system, announced in 2017, was one of the most widely covered astronomy stories in years, because it represented the possibility of not just 1, but 3 potentially habitable worlds in a single nearby star system. The James Webb Space Telescope has already begun to analyze the atmospheres of some of the TRAPPIST-1 planets, as well as those of other exoplanets. In 2023, Webb detected the presence of carbon dioxide in the atmosphere of an exoplanet called WASP-39b, the first time a specific molecule had been confirmed in an exoplanet atmosphere with such clarity. The ability to characterize exoplanet atmospheres in detail opens the possibility of detecting biosignatures, chemical signatures of life, in the atmosphere of a distant world. The most compelling potential biosignature would be the simultaneous detection of oxygen and methane, because these 2 gases react rapidly with each other and cannot coexist in significant quantities for long periods unless they are continuously replenished by some process. And the most likely such process on a world with the right conditions is biological activity. Proxima Centauri b is an exoplanet orbiting Proxima Centauri, the closest star to our Sun at just 4.2 light-years away. Discovered in 2016, it is an Earth-sized planet orbiting within the habitable zone of its host star. If Proxima Centauri b has a stable atmosphere, it could potentially have liquid water on its surface. However, Proxima Centauri is a red dwarf star, and red dwarfs are known for their frequent and intense flares, which could strip away a planet's atmosphere over time unless the planet has a strong magnetic field for protection. Whether Proxima Centauri b is truly habitable remains uncertain, but its proximity to Earth makes it one of the most scientifically interesting targets in the search for life beyond the solar system. The Drake equation, formulated by the astronomer Frank Drake in 1961, is a way of breaking down the question of how many communicating civilizations might exist in the Milky Way into a series of factors that can be estimated or investigated separately. It begins with the rate of star formation in the galaxy, multiplies by the fraction of stars that have planets, then by the average number of habitable planets per planetary system, then by the fraction of habitable planets where life actually arises, then by the fraction of living worlds where intelligence evolves, then by the fraction of intelligent civilizations that develop technology capable of interstellar communication, and finally by the average lifespan of such a civilization. Multiply all those factors together, and you get an estimate of the number of currently transmitting civilizations in our galaxy. The difficulty with the Drake equation is that for most of the factors, we have very little data. The early factors, the rate of star formation, and the prevalence of planets are now quite well constrained by observations. But the fraction of habitable planets where life arises, the fraction where intelligence evolves, and especially the lifespan of technological civilizations, are almost entirely unknown. Optimistic assumptions yield numbers in the thousands or millions. Pessimistic assumptions yield numbers close to 1 or even less than 1, meaning we may be alone in the galaxy. The Fermi paradox sharpens this question into its starkest form. The physicist Enrico Fermi, in a lunchtime conversation in 1950, reportedly asked a simple question. If intelligent life is common in the galaxy, and if any civilization a few million years ahead of us technologically could traverse the galaxy in a relatively short time on astronomical scales, why have we seen no evidence of anyone? The universe is old enough, and the galaxy large enough, that a civilization with enough of a head start could have spread across every star system by now. Where is everybody? The answers to the Fermi paradox range from the sobering to the genuinely frightening. Perhaps the development of intelligent life is so rare that we are in fact alone, or nearly so. Perhaps intelligent civilizations reliably destroy themselves before reaching the stage of interstellar travel, a possibility that carries obvious implications given the trajectory of human technology. Perhaps they exist, but for various reasons do not communicate in ways we can detect. Perhaps the galaxy is in fact teeming with life, but most of it is microbial and complex. Communicating intelligences are vanishingly rare. The Fermi paradox has no agreed solution, and the absence of any detected signal from another civilization is itself a data point of profound significance. On August 15, 1977, an astronomer named Jerry Amon was working as a volunteer on the SETI project at the Big Ear Radio Telescope at Ohio State University. He was reviewing printed data from the telescope's survey of the sky when he noticed a remarkable sequence of numbers and letters that indicated a signal roughly 30 times stronger than the background noise of the sky at a frequency close to the 21-centimeter hydrogen line, which had been proposed as a natural frequency for interstellar communication. The signal had lasted exactly 72 seconds, the maximum duration possible given the rotation of the Earth and the fixed beam of the telescope. It was so strong and so perfectly consistent with what a signal from an extraterrestrial source might look like that Amon circled it on the printout and wrote the word "wow" next to it. The WOW signal has never been detected again despite numerous attempts. Its origin remains unknown. It remains the strongest candidate for a non-terrestrial radio signal ever detected, and more than 4 decades later, it has not been explained. The search for life is not limited to signals from intelligent civilizations. Life on other worlds might be microbial, and microbial life leaves chemical signatures. On Earth, we have discovered life in the most extreme environments imaginable. Organisms called extremophiles thrive in environments that would kill most life. In the superheated water around hydrothermal vents on the ocean floor, in highly acidic conditions with pH levels close to 0, in saturated salt brines, deep in Antarctic ice sheets where liquid water has not flowed for millions of years, and in nuclear reactor cooling pools where radiation levels would be instantly lethal to most organisms. Tardigrades, tiny animals about 0.5 millimeter long, have survived direct exposure to the vacuum and radiation of open space in experiments conducted outside the International Space Station, making them the first known animals to survive in outer space. If life can survive the conditions found on Earth's most extreme environments, then the conditions found on Europa's ocean floor, on Mars's subsurface, in Titan's methane lakes, or in the clouds of Venus all become plausible habitats for some form of life. The discovery of life on any of these worlds, even simple microbial life, even the mere confirmation of life's chemistry without a living organism, would be one of the most consequential events in the history of science. It would tell us that life is not a unique accident that happened once on one planet in the history of the universe, but a phenomenon that arises wherever conditions allow. The history of human spaceflight is the story of a species reaching beyond its world for the first time, and it spans only a few decades. On October 4, 1957, the Soviet Union launched Sputnik 1, a metal sphere 83 centimeters in diameter containing a radio transmitter and a thermometer. It orbited Earth once every 96 minutes and transmitted a simple beeping signal that could be received by amateur radio operators around the world. Sputnik was not scientifically remarkable. Its importance was entirely symbolic. It demonstrated that a human-made object could be placed in orbit, and the fact that the Soviet Union did it first sent a shockwave through the Western world that accelerated the space race beyond anything previously anticipated. On April 12, 1961, the Soviet cosmonaut Yuri Gagarin became the first human being to travel in space. His spacecraft, Vostok 1, orbited Earth once in 108 minutes before re-entering the atmosphere. Gagarin ejected from the capsule at an altitude of approximately 7 kilometers and parachuted to the ground separately. This was not publicized at the time because the international rules for aviation records required that a pilot land with their aircraft, and the Soviets wanted Gagarin's achievement to count as an official record. He did not actually land in the spacecraft. The world was told he did. Gagarin himself said little about the discrepancy during his lifetime. Gagarin's flight electrified the global public and intensified the space race between the Soviet Union and the United States. President John F. Kennedy, in a speech before Congress in May 1961, committed the United States to landing a human being on the moon and returning them safely to Earth before the end of the decade. At the time, the United States had only 20 minutes of human spaceflight experience, a 15-minute suborbital flight by Alan Shepard 3 weeks earlier. The commitment was audacious to the point that many inside NASA privately doubted it was achievable in the time frame. 8 years later, it was done. On July 20, 1969, Neil Armstrong and Buzz Aldrin became the first human beings to set foot on the moon, while Michael Collins orbited above in the command module. Armstrong's first words from the lunar surface, "One small step for man, one giant leap for mankind," were heard by over 500 million people listening on radio and watching on television around the world. The mission, Apollo 11, brought back approximately 22 kilograms of lunar rock and soil. It proved that the moon was geologically distinct from Earth, resolving scientific debates about its nature and confirming the giant impact hypothesis for its formation. Apollo 13 launched in April 1970 and became the most dramatic crisis in the history of human spaceflight. 2 days into the mission, an oxygen tank in the service module exploded, disabling the fuel cells that powered the command module and venting the oxygen supply into space. The mission had to be aborted. The astronauts James Lovell, Jack Swigert, and Fred Hayes retreated into the lunar module, which had its own separate power and oxygen supplies, using it as a lifeboat for the return journey. Using the moon's gravity to slingshot the spacecraft back toward Earth, navigating by stars and landmarks rather than computer guidance, managing carbon dioxide levels with improvised scrubbers made from materials on hand, and enduring temperatures near freezing to conserve power, they returned safely to Earth 6 days after launch. The mission's flight director Gene Kranz later described the experience with the phrase he and his team had used during the crisis: "Failure is not an option." The Apollo program concluded with Apollo 17 in December 1972. 12 human beings walked on the moon across 6 missions. The program brought back approximately 380 kilograms of lunar material, deployed scientific instruments that continued to return data for years, and left retroreflectors on the lunar surface that are still used today to measure the precise distance to the moon by bouncing lasers off them. The moon is currently moving away from Earth at approximately 3.8 centimeters per year, and the retroreflectors have been used to measure this drift with extraordinary precision. The distance to the Moon is currently measured to an accuracy of about a centimeter. The International Space Station, the largest structure humans have ever placed in space, has been continuously inhabited since November 2, 2000. It orbits Earth at an altitude of approximately 400 kilometers, completing one orbit every 90 minutes, traveling at roughly 28,000 kilometers per hour. It is visible to the naked eye from Earth as a bright, steadily moving star crossing the sky in a matter of minutes. The ISS is a joint project involving NASA, the Russian space agency Roscosmos, the European Space Agency, the Japan Aerospace Exploration Agency, and the Canadian Space Agency. It has hosted astronauts and cosmonauts from 19 different countries and has been continuously inhabited for over 24 years. The scientific research conducted on the ISS has been extensive and consequential. Studies of the effects of long-duration spaceflight on the human body have revealed the detailed mechanisms of bone density loss, muscle atrophy, fluid redistribution, and vision problems associated with microgravity, and have driven the development of countermeasures used by current and future long-duration mission crews. Combustion behaves differently in microgravity, producing rounder, cooler flames with different chemical signatures, and this has implications for fire safety in spacecraft and for combustion efficiency research on Earth. Plant growth experiments have demonstrated the feasibility of growing food in space. The ISS has served as a platform for astronomical observations, Earth monitoring, dark matter detection experiments, and dozens of other scientific programs that cannot be conducted from the ground. NASA's Artemis program is the current initiative to return humans to the Moon, with the explicit goal of establishing a sustained human presence there and using the Moon as a proving ground for the eventual crewed missions to Mars. Artemis aims to land the first woman and the first person of color on the Moon, and to do so not as a one-time achievement, but as part of an ongoing program of exploration and resource utilization. The Moon's poles, particularly the permanently shadowed craters where water ice has been confirmed to exist, are of enormous scientific and practical interest. Water ice can be split into hydrogen and oxygen, providing both breathable air and rocket propellant, making the Moon a potential resupply station for missions to the outer solar system. SpaceX's development of reusable rocket technology has changed the economics of space access more dramatically than any development since the Space Shuttle. The Falcon 9 rocket pioneered the landing of orbital-class rocket boosters after launch, recovering them for reuse rather than discarding them in the ocean. This has dramatically reduced the cost of reaching orbit. The company's Starship vehicle, the largest and most powerful rocket ever built, is designed to be fully reusable and to carry both cargo and humans to the Moon, Mars, and potentially beyond. The ambition of sending humans to Mars within the coming decades, once considered science fiction, is now the stated goal of a growing number of national space agencies and private companies. The technical and engineering challenges remain enormous, but the trajectory of the technology over the past decade has demonstrated that timelines once considered optimistic are no longer impossible. If you have been with us through everything we have explored so far, through the solar system and its extraordinary worlds, through the life and death of stars, through the structure of galaxies and the mysteries of dark matter and dark energy, through the origin of the universe and the search for life, then you are ready for the final question. The one that everything else has been building toward. How does it end? The universe is not static. It is evolving, and the direction of its evolution, driven by the accelerating expansion powered by dark energy and the slow dimming of stars, points toward a future that is vast, cold, and dark almost beyond comprehension. But before the darkness, there will be deep time scales so long that the current age of the universe is a rounding error. The sun will become a red giant in approximately 5 billion years. The Milky Way will merge with Andromeda in approximately 4.5 billion years. These events are on the near horizon by cosmological standards. In roughly 10 to 100 trillion years, the last stars will stop forming. The current era, in which star formation is happening across the universe, is sometimes called the stelliferous era, from the Latin for star-bearing. It will end when gas clouds are no longer dense enough to form new stars, and the stars currently burning will exhaust their fuel one by one. The most massive stars will go first, in millions of years. The smaller stars will last tens of billions of years. The very smallest, the red dwarfs, which burn so slowly and so coolly that they are nearly invisible compared to stars like the Sun, will last for trillions of years. The last red dwarfs will not burn out until approximately 10 trillion years from now, approximately 700 times the current age of the universe. After the last stars die, the universe will enter what is called the degenerate era, a period lasting from roughly 10 to the power of 15 years to 10 to the power of 40 years, during which the only objects still intact are stellar remnants, white dwarfs slowly cooling to black dwarfs, neutron stars, and black holes. There will be no light sources, no warmth, no energy flowing through any star. The universe will be dark except for the occasional faint glow of a white dwarf not yet completely cooled, and the even fainter theoretical glow of Hawking radiation from black holes. Occasionally, brown dwarfs or white dwarfs in binary systems will collide or merge, producing brief flickers of energy against the darkness. But these events will become rarer and rarer as the universe spreads out and the density of matter decreases. Following the degenerate era comes the black hole era. By 10 to the power of 40 years, even white dwarfs and neutron stars will have been disrupted through quantum tunneling, processes, gravitational interactions, and possibly proton decay if that theoretical process occurs. The only objects remaining in the universe will be black holes of various sizes. The universe will be dark, cold, and extraordinarily sparse. Black holes will dominate the gravitational landscape, slowly evaporating via Hawking radiation over timescales proportional to the cube of their mass. A stellar mass black hole will take approximately 10 to the power of 67 years to evaporate completely. A supermassive black hole with a mass of 100 billion solar masses will take approximately 10 to the power of 100 years, a number written as 1 followed by 100 zeros, sometimes called a googol. At the end of the black hole era, the last supermassive black holes will release their final energy in a brief final burst of Hawking radiation, and then there will be nothing. No matter, no energy concentration, only a thin, cold gas of photons, electrons, and positrons growing ever more dilute as the universe continues to expand. This endpoint, called the heat death of the universe, is the most widely accepted fate based on current physics. It is the thermodynamic endpoint of a universe in which entropy increases monotonically and energy becomes ever more uniformly distributed until nothing useful can be done with it. It is not an explosion or a collapse. It is a fading, a cooling, a gradual unstoppable dilution of everything into nothing worth calling existence. There are alternative endings. The Big Rip is a scenario in which dark energy is not constant, but increases over time, eventually becoming strong enough to overcome not just gravity and the expansion of space, but the electromagnetic force, the nuclear forces, and ultimately even the bonds between atoms and atomic nuclei. In a Big Rip scenario, the universe ends in a finite time, somewhere in the range of 20 to 200 billion years from now, with every structure in the universe torn apart simultaneously, down to the subatomic level, as space itself rips open at every point. The Big Crunch is another possibility, although current observations make it seem unlikely given the accelerating expansion. If dark energy were to reverse, or if the universe contained enough matter to slow and reverse the expansion, the universe would eventually stop expanding and begin to collapse. Over billions of years, galaxies would merge, temperatures would rise, and the universe would end in a condition resembling the Big Bang in reverse, a final singularity of infinite density and temperature. The Big Bounce hypothesis suggests that such a collapse does not end in a final singularity, but instead triggers a new expansion, a new Big Bang, giving rise to a new universe. In this picture, the universe is cyclic, with big bangs and big crunches alternating endlessly, each universe born from the death of the one before it, with no beginning and no end to the cycle. If the Big Bounce is correct, then our universe is one chapter in an infinite book, and the Big Bang that created everything we know was not a beginning, but a transition. We do not know which of these fates awaits the universe. The current evidence favors the heat-death scenario, but our understanding of dark energy and of quantum gravity at extreme conditions is insufficient to be certain. The universe may hold surprises that our current physics cannot anticipate. Every time in the history of science that physicists have believed they were approaching a complete theory of everything, nature has revealed another layer of complexity beneath what they thought was the bottom. There is no reason to believe this process has ended. What is certain is this: the universe has already existed for 13.8 billion years. In that time, it has evolved from a hot, dense plasma into a vast, structured cosmos of 2 trillion galaxies, each containing hundreds of billions of stars, each star potentially hosting worlds, and at least one of those worlds hosting beings capable of looking up at the sky, of asking where all of this came from and where it is going, and of spending a night together following the question as far as it leads. The facts we have traveled through tonight, from the nuclear fires of the sun to the frozen silence of the Oort cloud, from the sulfuric clouds of Venus to the methane lakes of Titan, from the heartbeat of a pulsar to the event horizon of a black hole, from the first light after the Big Bang to the last breath of the last star, all of it is real. All of it exists or has existed or will exist. All of it can be known, at least in part, by the instrument you carry in your skull. The human mind, built by billions of years of evolution for the very practical purpose of surviving on one small planet, has nonetheless managed to reach across the entire observable universe and pull it into comprehension. That is, by any measure, the most extraordinary fact of all. Not the size of the universe, not the violence of its stars, not the mystery of its dark ingredients. The most extraordinary fact is that something inside it is aware of it, that the universe has, in at least one corner, folded back on itself and produced a witness. If this journey has been worth 5 hours of your night, like on this video, means more to us than you might think. And if you want to take the next one, subscribing means you will be there when we go. Thank you for being here. Sleep well. The universe is very large and very old, and it is not finished being discovered. The sun is also a dynamo, and the complexity of its magnetic behavior rivals anything else in the solar system. Beneath the visible surface, enormous convective cells of hot plasma rise and fall continuously, each one carrying heat from the interior to the surface and back again. These convective motions, combined with the differential rotation of the sun, which rotates faster at the equator than at the poles, continuously stretch, twist, and amplify the sun's magnetic field lines. Over the course of the 11-year solar cycle, this process winds the magnetic field into increasingly tangled configurations until the tension becomes too great and the field snaps into new arrangements, releasing energy in flares and reconfiguring the pattern of sunspots. At solar maximum, the magnetic field lines become so tangled that the sun essentially flips its polarity, with the north and south magnetic poles reversing. This flip takes roughly 11 years meaning the full magnetic cycle is actually approximately 22 years. The study of the Sun has been transformed in recent decades by a technique called helioseismology, which uses the vibrations of the Sun's surface to probe its interior structure in much the same way that seismologists use earthquake vibrations to probe Earth's interior. The Sun vibrates in millions of overlapping oscillation modes, with the surface rising and falling by small amounts on time scales of minutes. By measuring these oscillations with extraordinary precision, scientists have been able to map the Sun's internal structure, tracking how temperature, density, and the speed of sound vary with depth. Helioseismology has confirmed the basic theoretical picture of the solar interior and has revealed details that could not have been obtained any other way, including the depth and structure of the convective zone, the rotation rate at different depths, and the presence of flows beneath the surface that influence surface phenomena like sunspot formation. The neutrinos produced in the Sun's core provide another window into processes happening tens of thousands of kilometers below the visible surface. Neutrinos interact so weakly with matter that they pass through the entire body of the Sun almost without any interaction at all, escaping in approximately 2 seconds after being produced, compared to the tens of thousands of years it takes the energy they carry to reach the surface by radiation and convection. By detecting these solar neutrinos on Earth using specialized underground detectors, physicists can measure the rate of nuclear fusion reactions in the Sun's core almost in real time. In the 1960s, experiments found far fewer solar neutrinos than theoretical models predicted, a discrepancy known as the solar neutrino problem that puzzled physicists for decades. The problem was eventually resolved in the early 2000s when it was confirmed that neutrinos can change between different types during their flight from the Sun to Earth, a phenomenon called neutrino oscillation that required a revision of the standard model of particle physics. The Sun helped us discover new physics. The solar system's formation story has a chapter that many people are unaware of: the Nice model, a theory developed by planetary scientists in the early 2000s that proposes a dramatic rearrangement of the outer solar system approximately 4 billion years ago. According to this model, the giant planets did not form in their current positions. Jupiter, Saturn, Uranus, and Neptune formed closer together in a more compact configuration, and over hundreds of millions of years, gravitational interactions between the planets and with the disk of planetesimals surrounding them caused them to migrate outward into their current orbits. At a critical point in this migration, Jupiter and Saturn reached a gravitational resonance that sent them surging outward, scattering Uranus and Neptune and sending enormous numbers of objects from the outer disk inward into the inner solar system. This inward flux of objects may have been the cause of the late heavy bombardment, explaining why the Moon, Mercury, and other inner solar system bodies show a concentrated period of cratering approximately 4 billion years ago, rather than a smooth, continuous rate of bombardment. The Nice model, named after the city in France where it was developed, has been remarkably successful in explaining many features of the outer solar system that had previously been puzzling, including the orbital properties of Uranus and Neptune, the structure of the Kuiper belt, the distribution of the Trojan asteroids that share Jupiter's orbit, and the orbital characteristics of the inner solar system planets. It is not universally accepted, and several competing models have been proposed, but it represents a significant advance in our understanding of how the solar system reached its current configuration. The history of the solar system turns out to be far more dynamic and violent than the simple picture of planets forming in place and staying there. Mercury's relationship with time is one of the most peculiar of any object in the solar system. Because Mercury sits so deep in the Sun's gravitational well and orbits so close to it, the effects of general relativity are significantly stronger there than anywhere else in the solar system accessible to current spacecraft. Mercury's perihelion, the point in its orbit closest to the Sun, precesses, meaning it shifts position over time by a small amount with each orbit. For centuries, this precession was a mystery. Newtonian gravity predicted most of it, due to the gravitational influence of the other planets, but there was a small, unexplained residual. Einstein's general theory of relativity, published in 1915, predicted this residual exactly. The precession of Mercury's perihelion was one of the first observational confirmations of general relativity, and it remains a textbook example of how a subtle but measurable effect can distinguish between competing theories of gravity. Venus holds another extraordinary record that is easy to overlook. It is the brightest natural object in the night sky after the moon. Because Venus is closer to the sun than Earth, it passes through phases like the moon does, and at its crescent phase, when it is nearest to Earth and its illuminated side is only partially facing us, it can be bright enough to cast a faint shadow. Ancient peoples often saw Venus as two separate objects because it appears in the sky just after sunset in the evening and just before sunrise in the morning, and they called it both the evening star and the morning star before realizing it was the same object. The Greeks eventually recognized the two apparitions as identical and attributed the discovery to the philosopher Pythagoras, though the Babylonians appear to have known it even earlier. The atmosphere of Venus also produces a peculiar phenomenon called the ashen light, a faint glow sometimes reported by observers when the dark side of Venus is visible during its crescent phase. The ashen light is controversial. Some astronomers have reported seeing it over the centuries, and modern observations have occasionally detected it as well. The leading explanation is that it is caused by lightning in Venus's thick atmosphere, which could illuminate the dark hemisphere from within. If Venus experiences widespread lightning, it would be consistent with the intense atmospheric activity seen there. But confirming the ashen light as a real phenomenon, and not an optical illusion, has proven difficult. Venus still has mysteries that neither robotic orbiters nor landers have fully resolved. Mars has two moons, Phobos and Deimos, and they are among the most unusual natural satellites in the solar system. Both are tiny, irregularly shaped, and dark, resembling asteroids more than conventional moons. Phobos, the larger of the two, measures only about 27 kilometers across and orbits Mars at an altitude of just under 6,000 kilometers, completing one orbit in approximately 7.5 hours, much faster than Mars itself rotates. This means that from the surface of Mars, Phobos rises in the west and sets in the east, the opposite of every other moon in the solar system. And because its orbit is decaying due to tidal interactions with Mars, Phobos is slowly spiraling inward. In approximately 50 million years, it will cross the Roche limit and be torn apart by Mars's tidal forces, producing a ring around Mars similar to the rings of the outer planets. Mars, which currently has no ring, will acquire one within 50 million years at the cost of its largest moon. Deimos, the smaller and more distant of the two Martian moons, is only about 15 kilometers across and orbits at an altitude of about 23,000 kilometers. It takes about 30 hours to complete one orbit, which is just slightly longer than a Martian day, meaning it moves across the Martian sky extremely slowly. From the surface of Mars, Deimos would appear barely distinguishable from a star, a slow-moving point of light crossing the sky over 2.5 days. The origin of both Phobos and Deimos is debated. They may be captured asteroids from the nearby asteroid belt, or they may have formed from material ejected in an ancient giant impact on Mars, similar to the theory for the origin of Earth's moon. Their composition and structure, which will be studied in detail by Japan's Martian Moons Exploration Mission launched in 2024, may eventually resolve the question. Jupiter's magnetosphere, the region of space dominated by its magnetic field, is the largest structure in the solar system. If Jupiter's magnetosphere were visible to the naked eye from Earth, it would appear larger than the full moon in the sky, despite being more than 5 times farther away. The magnetosphere extends outward from Jupiter by approximately 63 Jupiter radii on the sunward side, roughly 4.5 million kilometers, and stretches into a tail extending hundreds of millions of kilometers away from the Sun. Within this vast magnetosphere, charged particles are accelerated to extremely high energies and concentrated in radiation belts far more intense than Earth's Van Allen belts. The radiation environment near Jupiter is intense enough to damage spacecraft electronics and would be rapidly lethal to any unprotected human being. This radiation challenge has been one of the primary engineering concerns for all Jupiter missions, including the Europa Clipper, which must be hardened to withstand the radiation environment it will encounter during its repeated close passes by Europa, which orbits deep within Jupiter's magnetosphere. The auroras on Jupiter are the most energetic in the solar system. They are driven not only by the solar wind, as Earth's auroras are, but also by the volcanic activity on Io. Io's volcanoes continuously eject sulfur dioxide and other materials into space, and this material becomes ionized and trapped in Jupiter's magnetosphere, forming a donut-shaped plasma torus around Jupiter in Io's orbital path. This plasma is continuously accelerated and channeled toward Jupiter's poles, where it produces permanent auroral ovals around both poles that are larger than the entire Earth. Jupiter's auroras glow primarily in ultraviolet and X-ray wavelengths, and they have been studied in detail by the Hubble Space Telescope and, more recently, by the Juno spacecraft, which has been orbiting Jupiter since 2016 and has made close, polar passes that have provided the first in-situ measurements of the aurora-producing particle populations. Saturn's moon system is one of the most scientifically diverse in the solar system, and its complexity is a reflection of the different environments that exist at different distances from Saturn and within and outside the ring system. In addition to the major moons, Titan, Enceladus, Rhea, Dione, Tethys, and Mimas, Saturn has dozens of smaller moons that play important roles in the structure and dynamics of the ring system. Mimas is perhaps Saturn's most distinctive small moon, at least visually. Its dominant feature is a giant impact crater called Herschel that is so large relative to the size of the moon that scientists have speculated that the impactor that created it may have come close to shattering Mimas entirely. The crater gives Mimas a striking resemblance to the Death Star from the Star Wars films, a resemblance that was noticed when the Voyager spacecraft returned, the first close-up images in 1980. Mimas also plays an important role in the ring system, as its orbital resonance with ring particles is responsible for the Cassini division, the prominent dark gap between the A and B rings that is visible even in small telescopes. Ring particles that orbit in the Cassini division would complete exactly 2 orbits for every 1 orbit of Mimas, and this resonance has swept the region relatively clear of particles over billions of years. Rhea, Saturn's second largest moon after Titan, made an extraordinary appearance in the scientific literature in 2010 when scientists analyzing data from the Cassini spacecraft proposed that Rhea might have its own faint ring system, which would make it the first moon ever confirmed to have rings. The evidence was indirect, based on unusual patterns in the electron and particle data collected as Cassini flew through the space around Rhea, suggesting the presence of material orbiting the moon. Subsequent observations failed to confirm the rings visually, and the question of whether Rhea has rings remains open. But the fact that a moon could potentially have its own ring system orbiting within the ring system of its parent planet adds another layer of complexity to an already extraordinarily complex system. The rings of Uranus were discovered in 1977, not by a spacecraft, but by a fortunate astronomical observation. On March 10, 1977, Uranus was due to pass in front of a distant star, a relatively rare event called a stellar occultation. Astronomers positioned around the world to observe the event noticed that the star blinked out and reappeared several times both before and after the main occultation by the planet itself, indicating the presence of narrow rings around Uranus that blocked the star's light. The rings of Uranus are very dark, much darker than Saturn's ice rings, and are composed of material that reflects only a few % of incident sunlight. They are also very narrow, some only a few kilometers wide, and they are kept narrow by shepherd moons similar to the ones that maintain Saturn's F-ring. Voyager 2 discovered additional rings and confirmed the existence of the shepherd moons during its 1986 flyby. The rings of Neptune were fully confirmed by Voyager 2 in 1989, though earlier stellar occultation observations had provided hints of their existence. Neptune's rings are faint and incomplete, with some of the rings appearing to have brighter arcs, denser concentrations of material within the ring. These arcs are unstable on astronomical timescales and should disperse into uniform rings within thousands of years, which means either they formed recently or they are being maintained by some mechanism, possibly the gravitational influence of nearby moons. The shepherd moon Galatea is thought to play a role in confining the ring arcs, but the precise mechanism is still not fully understood. The study of comets has undergone a revolution since the early 1980s, when the first close-up observations of comet nuclei were obtained. The Giotto mission to Halley's Comet in 1986 revealed a dark, irregularly shaped nucleus coated in a thick layer of very dark material, probably organic compounds, with jets of gas and dust erupting from specific active regions on the surface as they were heated by the sun. The activity of the comet was concentrated in these jets, rather than spread uniformly across the sunlit surface, suggesting that the surface of the nucleus is largely inactive, covered in a crust of material that insulates the ice beneath from solar heating. The Rosetta mission, launched by the European Space Agency in 2004, conducted the most detailed study of a comet ever attempted. After a 10-year journey that required 3 gravity-assist flybys of Earth and 1 of Mars to build up speed, Rosetta reached comet 67P/Churyumov-Gerasimenko in 2014 and entered orbit around it, becoming the first spacecraft to orbit a comet. For the next 2 years, Rosetta accompanied the comet on its journey toward the Sun and back, watching it transform from a quiet, frozen world in the outer solar system into an active comet with jets, outbursts, and a complex coma as it approached perihelion. In November 2014, Rosetta deployed the Philae lander, which became the first spacecraft to land on a comet's surface. The landing did not go entirely as planned, with Philae bouncing twice and coming to rest in a shadowed location that limited its solar power, but it still managed to transmit data for approximately 60 hours before its batteries ran out. The data returned by Rosetta revealed that Comet 67P has a highly complex shape, resembling 2 lobes connected by a narrow neck, suggesting it formed from the gentle merging of 2 separate objects early in the solar system's history. The comet's surface was found to be covered in boulders, pits, and cliffs, far more complex than the smooth, uniform surface that some models had predicted. And among the many molecules detected in the comet's coma were glycine, the simplest amino acid, and phosphorus, both of which are key ingredients for life as we know it. These detections added to the body of evidence suggesting that comets may have delivered some of the building blocks of life to the early Earth. The Orion Nebula, located approximately 1,300 light-years from Earth, is one of the most studied and photographed objects in the sky. It is the nearest large star-forming region to Earth, and at its heart lies a cluster of young, massive, hot stars called the trapezium, whose intense ultraviolet radiation illuminates the surrounding gas and dust, making the nebula glow. The Orion Nebula is visible to the naked eye as a fuzzy star in the sword of the constellation Orion. Binoculars reveal the faint glow of the nebula, and a telescope resolves the individual trapezium stars. Embedded within the Orion Nebula are hundreds of very young stars, many of them still surrounded by disks of gas and dust that may be in the process of forming planetary systems. These protoplanetary disks, called proplyds when seen silhouetted against the bright background of the nebula, give astronomers the opportunity to observe planetary formation in progress. Hubble Space Telescope images of the Orion Nebula revealed dozens of these proplyds in exquisite detail, showing disks of material around young stars that will eventually either form planets or be dispersed by the harsh radiation from the trapezium stars. The Orion Nebula is, in the most direct sense, a stellar nursery in action, a place where suns and solar systems are being built right now, at this moment, as you listen. The Hertzsprung-Russell diagram is one of the most important tools in astronomy, and understanding it is key to understanding how stars work. The diagram plots the luminosity of stars against their surface temperature, and when astronomers began constructing it in the early 20th century, they found that stars do not scatter randomly across the diagram, but instead fall into distinct groups. The vast majority of stars fall along a diagonal band called the main sequence, running from hot, bright blue stars in the upper left to cool, dim red stars in the lower right. Our Sun sits roughly in the middle of the main sequence. The position of a star on the main sequence tells you almost everything you need to know about it. Mass determines where on the main sequence a star falls, and mass determines how bright it burns, how hot its surface is, and how long it will live. The most massive stars, the blue supergiants, are so bright that they can be seen across enormous distances, but live for only a few million years. The least massive stars, the red dwarfs, are so faint that none of them are visible to the naked eye from Earth, despite the fact that red dwarfs are the most common type of star in the galaxy. But red dwarfs are extraordinarily long-lived, capable of burning steadily for trillions of years, far longer than the current age of the universe. The oldest red dwarfs alive today are essentially unchanged from the day they formed, because they have consumed only a tiny fraction of their available hydrogen in the time the universe has existed. Above the main sequence on the Hertzsprung-Russell diagram lie the giant and supergiant stars, stars that have evolved off the main sequence after exhausting their core hydrogen. Below the main sequence lie the white dwarfs, the remnants of dead sun-like stars. The diagram is a snapshot of stellar evolution, with each region corresponding to a different stage of stellar life. By studying where different populations of stars fall on the diagram, astronomers can determine the age of star clusters, trace the history of galaxies, and test models of stellar evolution with extraordinary precision. Variable stars are stars whose brightness changes over time, either because of physical changes within the star itself or because of the geometry of a binary system. Cepheid variable stars are among the most important objects in astronomy because their intrinsic brightness is directly related to the period of their variability. A cepheid that pulses with a period of 10 days is intrinsically brighter than one that pulses with a period of 5 days. And this relationship, first discovered by Henrietta Swan Leavitt at the Harvard College Observatory in 1912, provides a way to measure distances to objects far beyond what other methods can reach. Henrietta Swan Leavitt made her discovery while working as a human computer at Harvard, one of a group of women employed to analyze photographic plates of stars. Women at the time were not allowed to operate the telescopes or be considered full scientists, but they did much of the painstaking observational and analytical work that underpinned the discoveries that their male colleagues received credit for. Leavitt's discovery of the period luminosity relationship for Cepheids was one of the most important contributions to 20th century astronomy. It provided the tool that Edwin Hubble used in the 1920s to measure the distances to other galaxies and confirm that the universe extends far beyond the Milky Way, a discovery that transformed cosmology. The astronomical community later came to recognize the magnitude of Leavitt's contribution, but by then she had died of cancer in 1921, too early to see the full impact of her work. Binary star systems are far more common than single stars like our Sun. Surveys suggest that roughly half of all Sun-like stars are in binary or multiple star systems, with the fraction rising even higher for more massive stars. In a binary system, two stars orbit each other around their common center of mass, and the consequences of this mutual orbit can be extraordinary. If the stars are close enough, mass can flow from one to the other, dramatically altering the evolution of both stars. In a close binary where one star has already evolved into a white dwarf and the other is still on the main sequence or has expanded into a giant, the white dwarf's gravity can pull material from the companion star onto itself. This accreted material builds up on the surface of the white dwarf until it reaches a critical density and ignites in a nuclear explosion visible across vast distances, an event called a nova. Unlike a supernova, the white dwarf survives a nova explosion, and the process can repeat as material continues to accumulate. Some white dwarfs have been observed to undergo multiple nova explosions, making them recurrent novae. If the accreted material brings the total mass of the white dwarf close to the Chandrasekhar limit, approximately 1.4 solar masses, the white dwarf can no longer support itself against gravity and undergoes a runaway nuclear explosion that destroys it completely in a Type 1a supernova. Because this limit is essentially constant, all Type 1a supernovae reach approximately the same peak brightness, making them the standard candles used to measure cosmic distances and to discover the accelerating expansion of the universe. The fact that this constant and precisely calibrated explosion happens in binary systems throughout the universe has been perhaps the most consequential coincidence in the history of observational cosmology. Gravitational waves are ripples in the fabric of space-time, predicted by Einstein's general theory of relativity in 1916, but not directly detected until a century later. Einstein himself doubted that they would ever be detectable because the distortions they produce are so extraordinarily small. A gravitational wave from the merger of two stellar mass black holes a billion light-years away stretches and compresses space by a fraction of the diameter of a proton over a distance of several kilometers. The Laser Interferometer. Gravitational Wave Observatory, LIGO, consists of two facilities in the United States, one in Hanford, Washington, and one in Livingston, Louisiana. Each facility consists of an L-shaped interferometer with two arms 4 kilometers long. A laser beam is split and sent down each arm, reflected off mirrors at the end, and recombined. When a gravitational wave passes through, it stretches one arm while compressing the other by an infinitesimally small amount, causing the recombined light to interfere in a detectable way. The sensitivity required to make this measurement is beyond almost any other measurement ever attempted in science. On September 14, 2015, LIGO detected its first gravitational wave signal, caused by the merger of two black holes approximately 36 and 29 times the mass of the Sun, approximately 1.3 billion light-years away. The signal lasted approximately 0.2 of a second. The entire measurement, from the moment the signal entered the Livingston detector to the moment it entered the Hanford detector 7 milliseconds later, was completely consistent with the prediction of general relativity for a binary black hole merger. The discovery was announced in February 2016 and earned the Nobel Prize in Physics for Rainer Weiss, Barry Barish, and Kip Thorne in 2017. It opened a completely new field, gravitational wave astronomy, the ability to observe the universe through the distortions in space-time caused by its most violent events. Since that first detection, LIGO and its European partner Virgo have detected dozens of gravitational wave events, including binary black hole mergers, binary neutron star mergers, and systems where a neutron star merges with a black hole. Each event provides a clean measurement of the masses involved and the distance to the source, independent of any electromagnetic observations. The combination of gravitational wave detections with electromagnetic follow-up observations, called multi-messenger astronomy, is opening entirely new ways of studying the universe, and the field is still in its earliest days. The concept of a multiverse has entered mainstream scientific discussion, though it remains deeply controversial. Several independent lines of theoretical reasoning in modern physics lead to the possibility that our universe is not the only one. In the eternal inflation model, which is a variation of the cosmic inflation described earlier, the process of inflation never truly ends everywhere, but continues indefinitely in most of space, with local regions occasionally stopping their inflation and settling into states like our universe. In this picture, our universe is one bubble in an infinite froth of bubbles, each one a separate universe with potentially different physical constants. In the many worlds interpretation of quantum mechanics, every quantum event that could have multiple outcomes results in all outcomes actually occurring in separate branches of a branching universal wave function. Every time a particle decays or a measurement is made, the universe splits into versions in which each possible outcome occurred. In this interpretation, the universe we perceive is one of an incomprehensibly large number of parallel branches, each equally real. String theory, the leading candidate for a unified theory of all fundamental forces, predicts an enormous number of possible vacuum states, estimated at 10 to the power of 500, each with different physical constants. If string theory is correct, there is no reason why our universe should have the specific constants it has rather than any of the others, unless all of them are realized somewhere. The idea that all these vacua are realized in different parts of a multiverse provides one possible answer to the question of why the constants of nature are what they are. None of these multiverse scenarios have been tested, and some physicists argue they cannot, in principle, be tested, making them metaphysical rather than scientific propositions. Others argue that predictions which follow from a theory that has been tested in other ways inherit some degree of scientific status, even if the multiverse prediction itself is not directly accessible. The debate about the scientific status of multiverse theories is one of the most active in the philosophy of physics. But what it illustrates above all is that the question of whether our universe is unique or one of many is no longer purely a philosophical question. It is a question that modern theoretical physics takes seriously. The cosmic web is the name given to the large-scale structure of the universe, the arrangement of matter on scales of hundreds of millions to billions of light years. When mapped using surveys of millions of galaxies, the universe reveals an extraordinary structure, vast, empty voids hundreds of millions of light years across, surrounded by sheets and filaments of galaxies, with the densest concentrations of galaxies at the intersections of multiple filaments. This structure resembles, in some descriptions, a cosmic spider's web, or in other descriptions, the structure of a neural network, with filaments analogous to neurons and galaxy clusters analogous to synapses. The resemblance to biological neural networks has been noted by multiple scientists and has been the subject of formal statistical comparison. The comparison is suggestive, but the similarity is a matter of geometry rather than of any deeper connection. The voids in the cosmic web are not empty in the sense of containing no matter at all. They contain small numbers of galaxies, typically significantly less than the cosmic average density, and they are filled with the diffuse intergalactic medium, a thin gas of mostly hydrogen and helium that permeates all of space. The density of the intergalactic medium in voids is so low that if you were to gather all of it in a volume the size of a large building, you would not have enough atoms to make a single human cell. And yet, because the voids are so vast, this thin gas contains a significant fraction of the total ordinary matter in the universe. The filaments of the cosmic web are the highways of the universe. Galaxies form and move along these filaments, funneled by gravity toward the nodes where the filaments intersect. Galaxy clusters sit at these nodes, the densest places in the universe, containing hundreds to thousands of galaxies bound together by gravity and embedded in enormous halos of dark matter. The largest known structure in the observable universe, the Hercules Corona Borealis Great Wall, is a concentration of galaxy clusters forming a structure approximately 10 billion light-years long, approximately 1/10 the diameter of the observable universe. Its very existence challenges models of large-scale structure formation, because structures this large should not be able to form, given the current age of the universe and the rate at which matter can cluster under gravity. The James Webb Space Telescope, launched on December 25, 2021, represents the most powerful astronomical observatory ever placed in space. It orbits the Sun at a point called L2, approximately 1.5 million kilometers from Earth, always on the side of Earth facing away from the Sun. This location allows the telescope to keep its mirrors and instruments in perpetual shadow, cooled to temperatures near absolute zero, which is essential for its ability to detect the faint infrared light it is designed to observe. Webb was designed to look back to the earliest galaxies, to observe exoplanet atmospheres, to study the formation of stars and planetary systems, and to explore objects throughout our solar system. Its primary mirror is 6.5 meters across, nearly 3 times the diameter of Hubble's mirror, and it is made of 18 hexagonal segments coated with a thin layer of gold. The gold coating is not decorative. Gold is an excellent reflector of infrared light, which is the primary wavelength range Webb is designed to detect. The early results from Webb have exceeded expectations. Within weeks of beginning science operations in 2022, Webb returned images that pushed back the confirmed frontier of the observable universe, detecting galaxies that existed when the universe was less than 400 million years old. Some of these early galaxies were more massive and more mature than theoretical models had predicted, raising questions about how quickly galaxies can form and grow in the early universe. Webb also made the first direct measurement of carbon dioxide in an exoplanet atmosphere, as described earlier, and has begun to reveal details of the processes by which stars and planets form within dusty molecular clouds that were completely opaque to Hubble's optical observations. One of Webb's most ambitious long-term programs is the systematic study of potentially habitable exoplanets in the TRAPPIST-1 system. Determining whether any of these planets have atmospheres, and if so, what those atmospheres are made of, will take many years of careful observation. The signal from an exoplanet atmosphere is extraordinarily faint compared to the light from the host star, and detecting it requires combining many individual observations and performing highly precise subtraction of the star's contribution. But Webb has the sensitivity to do this work, and the results it will produce over the next decade or two may include the detection of molecules in an exoplanet atmosphere that cannot be explained by any known non-biological process, which would be the first serious candidate for evidence of life beyond Earth. The question of what life is, at its most fundamental level, is itself unresolved. The definitions offered by biologists tend to include characteristics like metabolism, reproduction, response to stimuli, and maintenance of homeostasis. But every definition has edge cases that make it awkward. Viruses are not clearly alive or dead by most definitions. Prions, misfolded proteins that can induce other proteins to misfold, reproduce, but have no metabolism. Fire meets many of the criteria for life, but is not considered alive. The difficulty of defining life is not just philosophical, it has direct, practical consequences for the search for life beyond Earth, because if we do not have a clear definition of what we are looking for, we may miss it or mistake non-life for life. One approach that has gained traction is to define life not in terms of its structure or components, but in terms of its function, the ability to undergo Darwinian evolution. Any system that can reproduce with heritable variation where some variations improve the system's ability to reproduce in its environment, will undergo natural selection and evolve. This functional definition sidesteps many of the edge cases and has the advantage of being, in principle, applicable to non-carbon-based, non-water-based systems. If we discovered on Titan a system of molecules capable of self-replication with heritable variation, most scientists would agree it was alive, regardless of whether it was made of methane-based chemistry rather than water-based chemistry. The question of how life began on Earth, called abiogenesis, is one of the deepest unsolved problems in science. We know that life was present on Earth approximately 3.5 to 3.8 billion years ago, based on the earliest fossil evidence of microbial mats. We know that the Earth is 4.5 billion years old. That leaves at most 1 billion years for life to have arisen from non-living chemistry, and possibly much less if the late heavy bombardment kept the surface sterile for much of the first 500 million years. The transition from chemistry to life, from collections of molecules to self-replicating, evolving systems, remains poorly understood despite decades of experimental work. The RNA world hypothesis is the leading current framework for understanding the origin of life. It proposes that before the current system of DNA, RNA, and proteins evolved, there was an earlier era dominated by RNA molecules, which can both store genetic information like DNA does and catalyze chemical reactions like proteins do. In this picture, the first life was self-replicating RNA molecules, and the more complex DNA protein system evolved later. Laboratory experiments have demonstrated that RNA molecules can spontaneously form under conditions that may have existed on the early Earth, that they can replicate themselves with some assistance, and that they can evolve in the laboratory when provided with appropriate selection pressure. But the gap between demonstrating these individual steps and assembling them into a coherent narrative of how life actually began remains large. The history of our understanding of the universe is itself one of the most remarkable stories in human intellectual history. For most of human existence, the sky was a source of wonder and mythology, but not of scientific knowledge. The planets were wandering lights with astrological significance. The fixed stars were the backdrop of the sky, permanent and unchanging. The Milky Way was a mysterious band of light. The sun and moon were gods, or the eyes of gods, or objects created specifically to serve humanity. The first major shift came with the ancient Greeks, who recognized that the Earth is a sphere, estimated its size with remarkable accuracy using the shadow it casts on the moon during lunar eclipses, and proposed that the planets orbit the Sun rather than Earth. The heliocentric model was proposed by Aristarchus of Samos in approximately 270 BC, nearly 2,000 years before Copernicus, but it was not widely accepted, partly because the astronomical observations available at the time could not clearly distinguish between a heliocentric and a geocentric model. The observational revolution began with Tycho Brahe in the 16th century, who spent decades making the most precise naked-eye astronomical observations in history, accumulating data on the positions of the planets with an accuracy of about 1 arc-minute. His data was inherited by Johannes Kepler, who spent years analyzing it and eventually derived his 3 laws of planetary motion, which described the shapes of planetary orbits and the relationship between a planet's distance from the Sun and the time it takes to complete one orbit. Kepler's laws were empirical descriptions that fit the data, but did not explain why the planets moved as they did. The explanation came from Isaac Newton, whose law of universal gravitation, published in 1687, provided the physical mechanism behind Kepler's empirical laws. Newton showed that the same force that causes an apple to fall from a tree is the force that holds the planets in their orbits. With a single mathematical framework, Newton unified terrestrial and celestial mechanics, demonstrating that the universe operates according to the same laws everywhere. Newton's mechanics held for over 2 centuries, until observations of Mercury's anomalous orbital precession and other puzzles accumulated into a crisis that was resolved by Einstein's general theory of relativity in 1915. Einstein's general relativity replaced Newton's picture of gravity as a force with a description of gravity as the curvature of space-time caused by mass and energy. In general relativity, a massive object like the Sun distorts the space-time around it, and other objects follow the straightest possible paths through this curved space-time, which from our perspective appear as curved orbits. The predictions of general relativity have been confirmed to extraordinary precision across a wide range of tests, from the bending of light by the Sun first observed during the 1919 solar eclipse, to the timing of signals from binary pulsars, to the gravitational wave detections of LIGO. General relativity is our current best description of gravity, but it is known to be incomplete because it breaks down at singularities and is incompatible with quantum mechanics. The search for a quantum theory of gravity, which would unify general relativity with the quantum field theory that describes the other three fundamental forces, is the central unsolved problem in theoretical physics. The Hubble Space Telescope, launched in 1990, transformed astronomy in ways that went far beyond the improvement in resolution that had been anticipated. Early images from Hubble were disappointing due to a flaw in the primary mirror, a shape error of just 2.2 micrometers, but the 1993 servicing mission corrected the optics and unleashed the telescope's full potential. Over the following 3 decades, Hubble made discoveries that reshaped our understanding of the universe. It measured the expansion rate of the universe with unprecedented precision, detected supermassive black holes at the centers of nearby galaxies, observed the light echoes from supernovae, revealed the structure of distant galaxies in the Hubble Deep Field images, and contributed to thousands of scientific papers across virtually every area of astronomy. The Hubble Deep Field obtained over 10 consecutive days in December 1995 by pointing the telescope at a tiny, apparently empty patch of sky near the Big Dipper, revealed nearly 3,000 galaxies in an area of sky smaller than a grain of sand held at arm's length. Almost every object in the image was a galaxy, each one containing hundreds of billions of stars, some of them so distant that their light had been traveling for over 12 billion years. The image was one of the most profound in the history of astronomy, not for what it showed, but for what it implied, that the universe is incomprehensibly full of galaxies in every direction to the limits of the observable universe. The search for exoplanets has moved beyond simply detecting whether planets exist around other stars to characterizing what those planets are actually like. The variety of planetary systems discovered in the past 3 decades has been far greater than most astronomers expected. We have found hot Jupiters, gas giants orbiting their stars in just a few days at temperatures of over 1,000 degrees. We have found super-Earths, planets between the size of Earth and Neptune with no counterpart in our own solar system. We have found mini-Neptunes, planets with thick hydrogen and helium atmospheres and liquid water potentially existing at their cores under enormous pressure. We have found rogue planets, planets that have been ejected from their home systems and drift through interstellar space with no star to orbit. We have found planets orbiting in binary star systems where 2 suns rise and set across the sky. We have found planets orbiting pulsars, the irradiated, radiation-blasted environments that seem like the last place one would look for worlds. We have found a planet orbiting a white dwarf, apparently one of the few survivors of that star's red giant phase. We have found planets in gravitational resonance chains, orbiting in precise mathematical relationships that speak to the dynamics of their formation. Every new survey, every new telescope, every new detection method has expanded the known diversity of worlds beyond what the previous generation of astronomers imagined. One particularly tantalizing category is the ocean world. Several exoplanets appear to have radii and masses consistent with being covered entirely by deep global oceans, possibly hundreds of kilometers deep, with no exposed land surface. On such worlds, the seafloor would be covered not by conventional water ice, but by high-pressure ice phases that form only at the enormous pressures found at the base of a deep ocean. Whether life could arise and sustain itself in such environments without any land surface and without the chemical exchanges between rock and water that are thought to be important for life on Earth is an open question. But the existence of ocean worlds in the galaxy makes the search for life there more diverse and interesting than if all potentially habitable planets were Earth-like in structure. The detection of radio signals from space is not the only way we might identify the presence of other civilizations. Astronomers have proposed searching for technosignatures, observational evidence of technology, in data from surveys of stars and galaxies. The waste heat produced by a civilization that uses energy extensively would produce an infrared signature detectable in principle by surveys of stellar infrared emission. A Dyson sphere, a hypothetical structure built by an advanced civilization to capture the full energy output of a star, would produce a very distinctive infrared signature with no optical light, essentially a star that had gone dark but was still radiating heat in the infrared. In 2015, the star KIC 846-2852, informally known as Tabby's star after astronomer Tabitha Boyajian, who led the research, attracted enormous attention because it showed strange, irregular dimming events unlike anything seen in other stars. The dimming sometimes reached 22% of the star's light, far more than any planet could produce, and the pattern was irregular and seemingly non-periodic. For a brief period, the possibility of a massive artificial structure in orbit around the star, perhaps a partially completed Dyson sphere, was seriously discussed. Subsequent detailed observations and analysis suggested that the dimming is more likely caused by clouds of dust and debris, possibly from the disintegration of a comet or an asteroid. But the case of Tabby's star illustrated how seriously modern astronomers take the possibility of technosignatures and how quickly observations can be reanalyzed through that lens. The interstellar medium, the gas and dust that fills the space between stars within a galaxy, is far from empty. It contains hydrogen in various forms, molecular clouds of complex organic chemistry, diffuse hot plasma from supernova remnants, magnetic fields, cosmic rays, and a variety of molecules including water, ammonia, formaldehyde, and even amino acid precursors. The study of the interstellar medium is important not just because it is the reservoir from which new stars and planets form, but because it is the medium through which the products of stellar evolution are transported and mixed. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that travel through the galaxy at nearly the speed of light. They originate from supernovae, active galactic nuclei, and other extreme astrophysical sources, and they continuously bombard the Earth's atmosphere, producing cascades of secondary particles detectable at the surface. Cosmic rays have been linked to the formation of clouds in Earth's atmosphere, suggesting a possible connection between solar activity, cosmic ray flux, and climate that is still being actively researched. The highest energy cosmic rays, detected rarely at ground level, have energies so extreme that they should be absorbed by interactions with the cosmic microwave background radiation before traveling more than about 160 million light-years, yet we detect them from sources whose origin is not clearly identified. These ultra-high-energy cosmic rays are among the most puzzling phenomena in high-energy astrophysics. The concept of habitability in astrobiology has expanded considerably from its early focus on surface liquid water. Scientists now recognize multiple distinct habitability niches, each relevant to different types of worlds and different types of life. The habitable zone around a star where liquid water can exist on the surface, the traditional focus, is sometimes called the circumstellar habitable zone, but there is also the concept of a galactic habitable zone, a region of the Milky Way where conditions are favorable for complex life, not too close to the violent galactic center with its intense radiation and frequent supernovae, and not too far from the metal-rich regions where Earth-like planets can form. The solar system sits comfortably within this galactic habitable zone. At the level of individual worlds, habitability depends not just on distance from a star, but on the planet's internal heat, its magnetic field, its geological activity, its atmospheric composition, its rotation rate, the presence of a large moon for tidal stabilization, and a host of other factors. Some scientists have proposed that Earth's specific combination of characteristics, including its large moon, its plate tectonics, its distance from both the galactic center and the Sun, and its position in a long-term stable period between ice ages, may be sufficiently unusual that complex multicellular life is rare even among technically habitable worlds. This view, sometimes called the rare Earth hypothesis, suggests that while microbial life may be common in the universe, the conditions necessary for the evolution of complex multicellular life may be extraordinarily restrictive. Others argue that evolution is robust and inventive enough that complex life would arise wherever simple life has time to evolve, and that the rare Earth hypothesis underestimates the adaptability of life. The history of life on Earth supports both views to some degree. Life arose quickly after the surface cooled, suggesting it is easy to start, but the transition from single-celled to multicellular life took approximately 2 billion years, suggesting that particular step may be difficult. The emergence of intelligence and technology took another 600 million years after that, and has apparently only happened once in the 4 billion-year history of life on Earth, suggesting it may be genuinely rare even on a biologically active world. The distance, scales involved in any potential interstellar communication or travel are almost paralyzing in their magnitude. The nearest star to the Sun, Proxima Centauri, is 4.2 light-years away. At the speed of the fastest spacecraft ever launched, the Parker Solar Probe at its closest solar approach, the journey would take approximately 60,000 years. Even at 1/10 of the speed of light, an engineering achievement that is far beyond anything currently conceivable, the journey would take 42 years. The galaxy is 100,000 light-years across. At 1/10 the speed of light, crossing the galaxy would take 1,000,000 years. Despite these distances, the concept of interstellar travel has been studied seriously by scientists and engineers. Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s, designed a theoretical uncrewed interstellar probe that could reach Barnard's star, about 6 light-years away, in approximately 50 years using nuclear pulse propulsion. The Breakthrough Starshot Initiative, announced in 2016 by a group including Stephen Hawking and Mark Zuckerberg, proposes launching gram-scale spacecraft on sails pushed by powerful laser arrays to 1/5 of the speed of light, potentially reaching Proxima Centauri in about 20 years. These are serious proposals backed by real physics, though the engineering challenges involved in building them are enormous, and the technology required does not yet exist. The idea of generation ships, large spacecraft carrying populations of humans on journeys lasting centuries or millennia, raises profound philosophical questions about identity, purpose, and community that go beyond the engineering challenges. A person born on a generation ship in transit to another star would live their entire life on a spacecraft, might die long before arrival, and would be making a journey whose goal they would never see. The descendants of the original crew who eventually arrived at the destination would be separated from the civilization that launched the ship by centuries of isolated development. The nature of their connection to humanity, and the ethics of making this decision for generations who cannot consent, are questions that science fiction has explored extensively, but that remain genuinely unresolved. The anthropic principle, in its weak form, states that the universe we observe must be compatible with the existence of observers capable of observing it. This seems trivially true, but has real implications. If the fundamental constants of nature, such as the strength of gravity, the masses of fundamental particles, or the energy density of the vacuum, were even slightly different from their observed values, the universe would be very different and, in most cases, hostile to the existence of any complexity, let alone observers. A universe with gravity slightly stronger would have collapsed long before stars could form. A universe with a slightly different ratio of matter to antimatter after the Big Bang might have annihilated entirely. A universe with a slightly larger cosmological constant would have expanded too rapidly for galaxies to form. This apparent fine-tuning of the constants of nature is one of the deepest puzzles in cosmology and physics. Several explanations have been proposed. One is that there is some deeper theory yet to be discovered that will explain why the constants have the values they have on the basis of some more fundamental principle. Another is the multiverse. If all possible values of the constants exist somewhere in an ensemble of universes, then it is not surprising that we find ourselves in a universe with constants compatible with our existence, because we could not exist in any other. A third is that the fine-tuning is not as fine as it appears, and that the landscape of possible universes compatible with some form of complexity is larger than current analysis suggests. The debate between these positions is one of the most philosophically charged in all of modern science. As we near the end of this journey, it is worth stepping back from the specifics and sitting with the overall picture that they assemble. We live on a small, rocky planet, the third of 8 in a solar system orbiting an average star, 2/3 of the way out from the center of a galaxy containing perhaps 300 billion other stars, in a universe containing 2 trillion such galaxies. We have been here, as a species, for approximately 300,000 years. We have had something recognizable as science for approximately 500 years. We have been exploring space with spacecraft for less than 70 years. We have been detecting gravitational waves for less than a decade. In that extraordinarily brief period of scientific activity, we have managed to work out the age and size of the universe, the mechanism by which stars shine, the origin and evolution of the chemical elements, the structure of the Milky Way, the existence of dark matter and dark energy, the formation of black holes, the propagation of gravitational waves, the ubiquity of exoplanets, the possibility of habitable moons in our own solar system, and the likely fate of everything billions of trillions of years from now. The fact that this has been accomplished by a species that, in evolutionary terms, is almost entirely unmodified from the one that was running from lions on the African savanna 100,000 years ago is itself one of the most remarkable facts in all of natural history. Science is sometimes described as a process of demoting humanity from the center of things. Copernicus removed Earth from the center of the solar system. Darwin removed humanity from a special, separately created category distinct from other animals. Hubble removed the Milky Way from the center of the universe. The discovery of the universe's vastness and age appears to make us insignificant. But there is another way to read the same facts. The vastness of the universe is not a rebuke to our significance. It is the context in which our existence and our curiosity about that existence become more extraordinary rather than less. The universe does not need to be aware of itself. Most of it is not. Most of it is empty space, or hot plasma, or cold rock, or the thin intergalactic medium drifting between galaxies. But here, in this particular corner of one particular galaxy, something happened that is, as far as we know, extraordinarily rare. Matter organized itself into forms capable of asking where they came from and where they are going, and then spent several centuries building instruments, developing mathematics, and making observations to find answers. That enterprise, imperfect and incomplete as it is is one of the most extraordinary things in the universe, and you have been part of it tonight. If this journey has been worth your night, a like on this video is the simplest and most direct way to tell us. And if you want to be here for the next one, subscribing takes 1 second but means we get to keep making this. Thank you. Sleep well. The universe is very large and very old, and it is still in every direction, full of things waiting to be discovered. The solar system contains far more than its 8 planets and their moons. Threading through the entire system, from the inner rocky worlds to the cold outer reaches beyond Neptune, is a population of smaller bodies whose diversity tells a richer story about the history of the solar system than the planets themselves. Among these are the centaurs, a class of small bodies with orbits that cross those of the outer planets, making them dynamically unstable on timescales of millions of years. Centaurs are believed to be Kuiper Belt objects that have been scattered inward by gravitational interactions with Neptune. Some of them display comet-like activity, with jets of gas and dust escaping from their surfaces even at the enormous distances from the Sun where they orbit, too far from the Sun for water ice to sublimate. The activity is thought to be driven by the sublimation of more volatile ices, like carbon monoxide and nitrogen, which can vaporize at the much lower temperatures found in the outer solar system. Trans-Neptunian objects, or TNOs, is the broad category that encompasses everything in the outer solar system beyond Neptune's orbit. Kuiper Belt objects, scattered disk objects, and detached objects. The most distant known TNOs have orbits that take them hundreds of astronomical units from the Sun and are not currently explained by the known planets. A pattern in the orbits of several extreme TNOs has led some astronomers to propose the existence of a large, undiscovered planet in the outer solar system, sometimes called Planet 9, with a mass of several Earth masses orbiting at distances of hundreds to perhaps 1,000 astronomical units. No direct observation of this hypothetical planet has been made, and the statistical case for its existence from the orbital clustering of extreme TNOs is debated, but the search for it is actively ongoing using large-format sky surveys. The scattered disk is a region of the outer solar system beyond and overlapping with the Kuiper Belt, populated by objects with highly eccentric orbits that extend far from the Sun at aphelion. Scattered disk objects are thought to have been scattered outward from the Kuiper Belt by gravitational interactions with Neptune, primarily during the period of planetary migration described by models like the Nice model. Eris, discovered in 2005, is the most massive known dwarf planet and a scattered disk object. Its discovery, along with several other large Kuiper Belt and scattered disk objects found in the early 2000s, was what prompted the International Astronomical Union to define the category of dwarf planet and to reclassify Pluto, which had been considered the 9th planet since its discovery in 1930. The relationship between the giant planets and the structure of the solar system is even more intimate than most people realize. Current models suggest that Jupiter may have initially formed beyond Saturn's position and then migrated inward, potentially as far as the current location of the asteroid belt, before migrating back outward. This hypothetical episode, sometimes called the Grand Tack model, would explain several puzzling features of the inner solar system. The small size of Mars relative to Venus and Earth, the depleted and chemically diverse asteroid belt, and the mixing of different types of asteroids that is observed in the belt today. As Jupiter moved inward and then back out, it would have scattered material through the inner solar system, truncating the disk of material that would otherwise have formed a larger Mars and delivering carbonaceous material from the outer solar system to the inner solar system in the process. Jupiter's present orbital resonances with other bodies in the solar system are a testament to its gravitational influence. The Trojan asteroids, two groups of asteroids that share Jupiter's orbit around the Sun, one group 60 degrees ahead of Jupiter and one 60 degrees behind, are trapped in stable gravitational configurations, called Lagrange points. There are estimated to be as many Trojan asteroids as there are asteroids in the main belt. NASA's Lucy mission, launched in 2021, is on its way to conduct the first survey of the Jovian Trojan asteroids, visiting 6 different Trojans between 2025 and 2033. These primitive objects are believed to be preserved remnants of the material that built the outer solar system, and studying them in detail may reveal information about conditions in the early solar system that cannot be obtained any other way. Saturn's Titan is so Earth-like in its atmospheric processes that it has been described as a natural laboratory for studying early Earth chemistry, before the rise of photosynthesis transformed Earth's atmosphere from a nitrogen-methane mixture to the nitrogen-oxygen mix we breathe today. The organic molecules produced in Titan's atmosphere by ultraviolet photochemistry rain down onto the surface continuously, building up a global layer of organic sediment. On a geological timescale, Titan may have accumulated an enormous organic reservoir. If Titan's interior contains liquid water, even temporarily, the organic materials on the surface might come into contact with the water and undergo chemical reactions relevant to the origin of life. Several scenarios for how this might happen have been proposed, including impacts that briefly melt the surface ice, cryovolcanic eruptions that bring liquid water to the surface, or slow diffusion of liquid water through the ice crust. Whether any of these scenarios operate on Titan, and whether any resulting chemistry is relevant to the origin of life, is a question that the Dragonfly mission and subsequent missions may eventually be able to address. The search for biosignatures on Venus has recently attracted renewed attention. In September 2020, a team of astronomers announced the detection of phosphine in Venus's atmosphere at an altitude where temperatures and pressures are roughly Earth-like. Phosphine is a molecule that on Earth is produced predominantly by biological processes and by industrial chemistry, and there is no known abiotic process that should produce it in the quantities apparently detected in the Venusian atmosphere. The announcement generated intense interest and immediate controversy. Subsequent reanalysis of the data raised questions about the statistical significance of the detection, and the claimed abundance was revised downward substantially. As of now, the detection remains unconfirmed and contested, but it has reignited interest in Venus as a target for astrobiology. The cloud layer of Venus, at altitudes between 45 and 65 kilometers, is the most Earth-like environment in the solar system outside of Earth itself, with temperatures ranging from 0 to 70 degrees Celsius and pressures comparable to Earth's surface. Some scientists have proposed that life might have originated on Venus billions of years ago, when the planet may have had liquid water on its surface, and that some microbes could have survived the transition to the hellish present conditions by retreating into the cloud layer where conditions are more temperate. Ganymede, Jupiter's largest moon and the largest moon in the solar system, is in many ways a world deserving its own chapter. Larger than Mercury, Ganymede is the only moon known to have its own internally generated magnetic field, created by convection in its liquid iron core, similar to the mechanism that generates Earth's magnetic field. Ganymede's magnetic field creates its own miniature magnetosphere, embedded within Jupiter's enormous magnetosphere, producing auroras at Ganymede's poles that have been observed by the Hubble Space Telescope. The Galileo spacecraft confirmed that Ganymede also has a subsurface ocean, and recent analysis of Hubble data suggests that this ocean may be enormous, possibly 1,000 kilometers deep, containing more liquid water than all of Earth's oceans combined. The ocean is sandwiched between layers of ice above and below, rather than being in contact with a rocky seafloor, which may limit the chemical exchanges that are thought to be important for supporting life. But the sheer volume of liquid water, the duration over which it has likely been present, and the complexity of Ganymede's geology make it a world of considerable astrobiological interest. Callisto, the outermost of the Galilean moons, presents a stark contrast to its inner companions. Where Io is violently active, and Europa and Ganymede show evidence of geological processing, Callisto's surface is the most heavily cratered in the solar system, a record of every impact it has suffered since the solar system formed. No geological activity has resurfaced Callisto in 4.5 billion years. Yet evidence from the Galileo mission suggests that Callisto too may have a subsurface ocean, maintained at depth by antifreeze components like ammonia in the water. Callisto is the only Galilean moon not caught in the orbital resonance chain that drives tidal heating in Io, Europa, and Ganymede, which is why it has been geologically quiet while its inner companions have remained active. The possibility that even a geologically dead world like Callisto might harbor a liquid water ocean underscores how widespread liquid water environments may be in the outer solar system. The far study of meteorites has provided some of the most direct information about the early solar system. Meteorites are pieces of asteroids and occasionally of Mars and the Moon that have survived passage through Earth's atmosphere and landed on the surface. They are classified into several types based on their composition and the degree to which they have been altered since their formation. Chondrites are the most primitive meteorites, composed of material that dates back to the formation of the solar system and has undergone little subsequent processing. Carbonaceous chondrites, the most chemically complex type, contain amino acids, nucleobases, sugars, and other organic molecules, as well as pre-solar grains. Tiny particles that formed in ancient stars before the solar system existed and were incorporated into the molecular cloud from which the solar system formed. These pre-solar grains carry isotopic signatures that identify them as coming from specific types of stars, including red, giant stars, massive stars that ended in supernovae, and asymptotic giant branch stars. Some of these grains are older than the solar system by billions of years. Holding a piece of carbonaceous chondrite in your hand means holding material that formed in stars that lived and died before the sun was born, material that drifted through the galaxy for billions of years before being swept up into the protoplanetary disk and eventually incorporated into an asteroid, which survived intact for 4.5 billion years, fell to Earth, and was picked up by a scientist. The geological and cosmic history embedded in a single meteorite is staggering. The auroras of the outer planets are among the most dramatic in the solar system, and they are driven by mechanisms quite different from Earth's familiar northern and southern lights. Jupiter's auroras, described earlier, are permanent features powered partly by material from Io. Saturn's auroras are similarly spectacular, driven by interactions between the solar wind and Saturn's magnetic field, with some contribution from material venting from Enceladus. But the auroras of Uranus and Neptune have been detected and studied only at a limited level, due to the lack of spacecraft at either planet since Voyager 2's brief flybys. Uranus's auroras are particularly unusual because of the planet's extreme axial tilt and the unusual orientation of its magnetic field. Unlike most planetary magnetic fields, which are roughly aligned with the planet's rotation axis, Uranus's magnetic field is tilted by about 60 degrees from the rotation axis and is also offset from the planet's center. This creates a magnetic field configuration that wobbles dramatically as Uranus rotates, causing the auroras to move across the planet in complex patterns that have no equivalent on any other world. The Hubble Space Telescope has detected Uranus's auroras in the ultraviolet, and their complex morphology continues to be studied by astronomers hoping to understand how Uranus's unusual magnetic field interacts with the solar wind and with the planet's own magnetosphere. The concept of terraforming, the deliberate modification of a planet's environment to make it habitable for human life, has been discussed seriously by scientists and engineers for decades, particularly in the context of Mars. Mars is considered the most promising terraforming candidate because of its proximity, its day length similar to Earth's, its seasons, and the availability of frozen water at the poles and in the soil. Full terraforming of Mars would require dramatically increasing the atmospheric pressure and temperature and introducing liquid water on the surface. The most commonly discussed approach involves releasing greenhouse gases to warm the planet, which would vaporize the carbon dioxide frozen at the South Pole and create a feedback loop of warming. Once temperatures rise above freezing, melting permafrost would release additional greenhouse gases. Over timescales of centuries to millennia, the atmosphere could theoretically become thick enough for liquid water to exist on the surface, though the oxygen content would still need to be increased substantially before humans could breathe the air. The ethical dimensions of terraforming are significant. If Mars has any existing life, even microbial life living in subsurface protected environments, altering the planet's environment to suit human needs might destroy it before we have even confirmed its existence. The scientific case for exploring Mars thoroughly and understanding its biology, if any, before any terraforming efforts would be overwhelming. Beyond Mars-specific considerations, the broader question of whether humanity has the right to alter other worlds and whether doing so is in any sense desirable is a question that planetary protection philosophy and space ethics are only beginning to engage with seriously. The search for the most massive objects in the universe leads ultimately to the question of quasars. Quasars, short for quasi-stellar objects, were discovered in the early 1960s as radio sources that appeared point-like in optical telescopes, like stars, but whose spectra showed enormous redshifts indicating they were billions of light years away. At those distances, their apparent brightness implied that they were emitting more energy than entire galaxies from regions smaller than the solar system. The energy source was eventually identified as accretion of matter onto supermassive black holes, the same process that drives active galactic nuclei more generally. Quasars are the most luminous, sustained sources of energy in the universe, outshining their host galaxies by factors of hundreds or even thousands. Quasars were much more common in the early universe than they are today. The quasar epoch peaked approximately 10 to 12 billion years ago, when the universe was young and supermassive. Black holes at the centers of young galaxies were growing rapidly by accreting the abundant gas in their surroundings. As galaxies evolved and the gas was consumed or expelled by the energy from the quasar itself, the fuel supply for the black hole was reduced and the quasar activity declined. Most of the supermassive black holes that once powered quasars are now relatively quiet, including Sagittarius A star at the center of the Milky Way. The evidence for quasar activity in the distant universe is itself a kind of fossil record, showing us what the universe looked like when it was young and its black holes were still growing. Looking at a quasar 10 billion light-years away means looking at a time when the universe was less than 4 billion years old, when the Milky Way was still assembling itself, and when the first generations of stars had already enriched the universe with the heavy elements needed for rocky planets. Gravitational lensing is the bending of light from distant objects by the gravitational field of massive objects between them and the observer, an effect predicted by general relativity. It was first confirmed observationally during the 1919 solar eclipse, when stars near the edge of the sun appeared slightly displaced from their true positions due to the bending of their light by the sun's gravitational field. The confirmation of this prediction by Arthur Eddington's expedition to observe the eclipse from the west coast of Africa made Einstein famous overnight, with newspapers around the world reporting that the prediction of the reclusive German physicist had been confirmed. Einstein himself had apparently predicted this level of reaction and left a note for his assistant before the results were announced. Good news! Gravitational lensing on cosmological scales produces spectacular effects. When a massive galaxy or cluster of galaxies lies between Earth and a more distant galaxy, the mass of the foreground object can bend the light from the background galaxy, producing distorted, stretched, or even multiple images of the background object. The most extreme cases, where the alignment is nearly perfect, produce Einstein rings, complete circular arcs of light surrounding the lensing object. The gravitational lensing effect can magnify the light from very distant galaxies by factors of 10 to 100, allowing astronomers to study objects that would otherwise be too faint to detect. Some of the most distant galaxies ever observed have been found by using galaxy clusters as natural gravitational telescopes, with the cluster's mass acting as an amplifying lens. The combination of the James Webb Space Telescope with gravitational lensing from massive foreground clusters has allowed astronomers to observe galaxies in the first few hundred million years of the universe's history in extraordinary detail. The Voyager probes deserve a more extended reflection than we gave them earlier in this journey, because they represent something unique in the history of exploration. The first human-made objects to enter interstellar space, and the most distant human-made objects from Earth, and they are still out there, still transmitting, almost 50 years after their launch. Voyager 1 was launched on September 5, 1977, and Voyager 2 on August 20, 1977. Despite Voyager 2 launching first, Voyager 1 followed a faster trajectory and reached Jupiter first. The grand tour that the Voyagers accomplished, using gravitational assists from each outer planet to slingshot towards the next, was only possible because of a rare planetary alignment that occurs approximately every 175 years, a window that NASA recognized and took advantage of with remarkable foresight and technical skill. Had they missed the window, the next opportunity would have been in the 22nd century. Voyager 1 made close flybys of Jupiter in 1979 and Saturn in 1980, discovering the active volcanoes of Io, the complexity of Jupiter's atmosphere, the detailed structure of Saturn's rings, and the atmosphere of Titan. After the Saturn flyby, Voyager 1's trajectory was directed upward out of the plane of the solar system, ending its planetary observations. Voyager 2 followed a different trajectory, making close flybys of Jupiter, Saturn, Uranus, and Neptune in sequence, completing the first and still only tour of all 4 outer planets in a single mission. The images and data returned by the Voyagers transformed our understanding of the outer solar system almost overnight. Both Voyagers carry a golden record, a 12-inch gold-plated copper disc containing sounds and images of Earth, intended as a message to any extraterrestrial civilization that might someday intercept the spacecraft. The records contain greetings in 55 languages, 116 images depicting Earth and humanity, 90 minutes of music from various world cultures, including Bach, Beethoven, and Chuck Berry, and sounds ranging from a mother's first words to her child, to thunder, wind, surf, and the sounds of birds and whales. The records were produced under the direction of Carl Sagan, who considered the project both a scientific gesture and a cultural one, an expression of human ambition and goodwill directed toward the unknown. Voyager 1 crossed the heliopause, the boundary between the solar wind and the interstellar medium, in August 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November 2018. As of 2024, Voyager 1 is approximately 24 billion kilometers from the Sun, and its radio signals, traveling at the speed of light, take approximately 22 hours to reach Earth. The probe is still returning scientific data about the properties of the interstellar medium, measurements that no other spacecraft has ever made. The fact that something launched by human beings in 1977 is now measuring the properties of the space between the stars and is still communicating with Earth is one of the most remarkable achievements in the history of exploration. The New Horizons mission to Pluto and the Kuiper Belt represents the closing of a chapter that opened in 1930, when Clyde Tombaugh discovered Pluto as a faint, moving point of light on photographic plates. For 85 years, Pluto was known only as a point, with no surface detail visible even from the most powerful Earth-based telescopes. The New Horizons spacecraft changed that in a matter of hours. The images it returned showed a world of extraordinary complexity, with towering water ice mountains, glaciers of flowing nitrogen ice, plains resurfaced by geological activity within the last 100 million years, and a haze-filled atmosphere with multiple layers of organic chemistry extending hundreds of kilometers above the surface. After its Pluto flyby, New Horizons was redirected toward a Kuiper Belt object known as Arrokoth, which it reached in January 2019. Arrokoth turned out to be a contact binary, two roughly spherical lobes that had gently merged long ago, giving it a shape resembling a snowman or a reddish peanut approximately 35 kilometers long. Its smooth, undisturbed surface and red color, from organic compounds called tholins, make it one of the most primitive objects ever directly observed. Arrokoth formed in the calm, cold outer reaches of the protoplanetary disk, far from the violent collisions of the inner solar system, and it appears to have changed remarkably little since the solar system was young. It is as close to an untouched relic of the solar system's birth as anything yet visited by a spacecraft. The scale of the universe creates a philosophical problem that has been discussed by astronomers, philosophers, and thoughtful people generally since the telescope first revealed that the universe was larger than anyone had imagined. The problem is simply this: how do you assign meaning to human life, human history, and human experience in a universe 13.8 billion years old, 93 billion light-years, across, containing 2 trillion galaxies, the vast majority of which will never be visited by any being from Earth? Various answers have been offered. One is that meaning does not require scale, that the significance of an event or a life is not a function of how large a fraction of the universe it occupies. A human life is no less significant for being small relative to a galaxy than a symphony is less significant for lasting 90 minutes rather than a billion years. Another answer is that the rarity of intelligence, if it is indeed rare, makes each instance of it cosmically significant regardless of its physical scale. If beings capable of asking questions and finding answers are vanishingly uncommon in the universe, then their existence is not trivialized by the size of the universe, but is instead precious in proportion to it. A third answer, which does not contradict the others, is that contemplating the universe at its full scale is itself a form of meaning, perhaps the highest form available to beings like us. The astronomer Carl Sagan wrote that we are a way for the cosmos to know itself. The idea is that when a human being looks up at the night sky and understands, even partially, what they are looking at, the universe is, through that person, becoming aware of itself. The atoms in your brain, forged in stellar furnaces billions of years ago, arranged by the blind processes of evolution into a structure capable of comprehending those same stellar furnaces, represent something that did not exist before life and intelligence arose. Whether that seems meaningful is a personal judgment, but it is at least a fact. Space exploration has always been as much about what we discover about ourselves as about what we discover about the universe. The photographs of Earth taken from space have had a documented effect on those who have seen them, both the astronauts who saw them directly and the billions who saw them in photographs and broadcasts. The first Earthrise photograph, taken by astronaut William Anders during the Apollo 8 mission in December 1968, showed Earth as a small, fragile blue sphere rising above the gray lunar surface, the only color in a vast gray and black field. The image became one of the most widely reproduced photographs in history and is credited by some environmental historians as a catalyst for the modern environmental movement, giving people their first visceral sense of Earth as a single, bounded, vulnerable place. The pale blue dot photograph, taken by Voyager 1 in February 1990 at Carl Sagan's request, shows Earth as a tiny point of light, less than a pixel across, suspended in a sunbeam against the blackness of space, photographed from a distance of approximately 6 billion kilometers. Sagan's description of the image in his 1994 book of the same name remains one of the most eloquent passages ever written about the human condition in the context of the cosmos. He wrote about the delusion that humanity occupies a privileged position in the universe, about the pointlessness of all the rivers of blood spilled to make some momentary conqueror the master of a fraction of a dot, and about the responsibility this perspective places on us to deal more kindly with one another and to preserve and cherish this pale blue dot, the only home we have ever known. Whether you find this perspective humbling or inspiring, or both simultaneously, is up to you. But the fact that we have the photographs, the fact that human beings built spacecraft that flew far enough to take them, and the fact that we look at them and feel something, all of this is a reminder that space exploration is not merely a scientific enterprise. It is a cultural one. It changes how we see ourselves and our place in the universe, and it always has, from the first night that a human being lay on their back and looked up at the stars and wondered what they were. In the coming decades, humanity's relationship with space will change in ways that are difficult to predict precisely, but whose broad outlines are becoming visible. Crewed missions to the moon are being planned and executed by multiple nations. The first human beings to set foot on Mars may already be alive today. Space tourism, once science fiction, is already a commercial reality for those who can afford it. Large constellations of satellites are changing the night sky in ways that astronomers are still assessing. The question of how to govern activities in space, including the extraction of resources from asteroids and the moon, and the long-term settlement of other worlds, is moving from philosophical discussion to practical policy negotiation. The commercialization of space access has dramatically lowered the cost of reaching Earth orbit and has enabled a new generation of scientific missions that would not have been economically feasible under the traditional government-funded model. Small satellites the size of a loaf of bread, called CubeSats, are being used for Earth observation, communications, and scientific research by universities and small companies that could not previously participate in space science. New companies are developing spacecraft for lunar missions, Mars missions, and asteroid mining, operating in parallel with the traditional space agencies and in many cases partnering with them. The possibility of detecting biosignatures in an exoplanet atmosphere within the next 1 to 2 decades is realistic, depending on what the James Webb Space Telescope and its successors find. If such a detection is made, the implications will extend far beyond astronomy, touching philosophy, religion, sociology, and every field that involves the question of humanity's place in the universe. The detection would not confirm intelligent life or complex life or any life we would recognize. It would confirm that on some world orbiting some distant star, the chemistry of life, or something that functions like it, is changing the composition of an atmosphere. But that would be enough to change everything. There is a quality to the night sky that no description fully captures, something that is felt rather than understood, and that astronomers and laypeople alike report experiencing when conditions are right. It requires darkness, away from the artificial glow of cities and towns. It requires patience, enough time to let the eyes adapt to the dark and the mind to quiet down from the noise of the day. And it requires looking up, not scanning for anything in particular, just looking. What you see on a clear night far from city lights is not just a collection of stars and planets. It is depth, the nearest. Stars are a few light years away. The ones slightly fainter are tens or hundreds of light years. The faint band of the Milky Way is the disk of the galaxy, stars so distant they blur into a continuous glow. And if the conditions are right, you can see Andromeda with the naked eye, 2.5 million light-years away, the most distant object visible without optical aid. You are not looking at a flat screen of light. You are looking into three-dimensional space, time as well as distance, because the light from the farthest things has been traveling longer. There is a word in Welsh, hiraeth, that refers to a kind of longing for something you cannot quite name or reach, a homesickness for a home you may never have had. Some people who spend time under a truly dark sky describe something like this in response to it, a longing for those distances, for the universe as it is, rather than as human civilization has made it. Whether that feeling points to something real about our nature, something in us that evolved alongside fire and open sky and knew the stars before it knew streets, is a question for psychologists and philosophers. But the fact that it exists, that the sky can move people in this way, tells us something about the relationship between human beings and the cosmos that no telescope can quite capture. We have covered an enormous amount of ground in this journey. We have visited the nuclear heart of the Sun and the frozen edge of the Oort cloud. We have descended into the metallic hydrogen interior of Jupiter and skimmed the methane lakes of Titan. We have watched stars be born in nebulae and die in supernovae. We have explored the event horizons of black holes and the gravitational wave detections that opened a new era of astronomy. We have traced the universe back to its first moments and followed it forward to its cold and silent end. And we have asked, without yet receiving a definitive answer, whether we are alone. The universe is not indifferent, to us in the sense that would make indifference painful. It is simply vast, old, and operating according to laws that do not have opinions about what they produce. But what those laws have produced here, in this corner of this galaxy, at this moment in cosmic history, is extraordinary by any standard. Matter that began as hydrogen and helium in the first minutes after the Big Bang has, over the course of 13 billion years, organized itself into structures capable of understanding their own history. That is not small. That is not insignificant. That is, in any honest assessment, one of the most remarkable things in the known universe. The story is not finished. New telescopes are being built. New missions are being planned and launched. New generations of scientists, some of them children right now, will make discoveries we cannot anticipate, using tools that do not yet exist, to answer questions that have not yet been asked. The universe has been here for 13.8 billion years and will be here for incomprehensibly longer. We are very early in the story of intelligent life trying to understand it, and the most important chapters have almost certainly not been written yet. The sky above you right now is full of the light from 2 trillion galaxies. Most of it is too faint to see without a telescope. But it is there. All of it is there. It has been traveling toward you for millions and billions of years, and tonight it arrived. Sleep well. Dream of what is out there. And when you wake up, the universe will still be waiting.